Good morning, everyone. Welcome to our RemTech 2021 webinar series. Thank you for joining us today. Today's webinar is sponsored by Trace Associates. Thank you to Trace for your continued support. We have 8 presentations today. Each are 25 minutes long with a couple. We'll do time for a couple questions after each. Then we'll move right into the next presentation. And at about 10:30, we'll take a 15-minute break for everyone to stretch their legs, grab a coffee, check your messages, and then we'll jump back in and do the next 4 presentations. Before we get started, just a reminder, we have 2 more webinars in this series on November 25th and December 2nd. If you have signed up for this one, you'll receive links for the other 2 closer to the dates. You don't need to re-register. Our EnviroTech is coming up on April 20th to 22nd in Calgary. And as you've probably heard, RemTech East is happening. It'll happen every 2nd year, and the regular RemTech will continue every year in Banff. But RemTech East will be June 1st to 3rd in Falls View Casino, Niagara Falls. The call for abstracts is currently up. I encourage you to do that. So our first presentation today is Anthony Aquino with Agate Labs on new methods to more accurately quantify hydrocarbon contamination from natural backgrounds. I'll turn it over to Anthony. To share his presentation, and we'll get started. Anthony, are you there?
Yep, I'm there. Sorry.
Okay.
I was just waiting for things to load. All right. As Joe said, my name is Anthony Aquino. I work in the forensic department of Agate Labs, and for the past 2 or so years, I've been working on the 2D GC we have in the lab and working on new methods for it to be used. So that's my presentation about new methods to more accurately quantify hydrocarbon contamination from natural background. So a brief overview on what my presentation will be. I'll briefly discuss environmental forensics, and then I'll discuss the GCGC, or 2DGC as we call it, its principles, its benefits, its uses, and then look at some outputs and analyses. Then I'll get into our biogenic analysis by GCGC FID, first the method of analysis, and then a couple project examples of analysis we've done for this. And then I'll look at our future work, what we want to continue doing with this method. So environmental forensics reconstructs events in the environment using defensible scientific methods to differentiate between complex compounds found in the environment. This provides information about the compounds present and the underlying chemistry. This information can be used to determine many things. Was the site contaminated by current activities or from some other source? Was the site contaminated by a previous owner or user? When did the contamination occur? And is the contamination due to natural processes, biogenic, or a natural spill, which would be petrogenic? And is there more than one source present in the contamination? And all of these things can be deduced and figured out using different methods in the forensics lab. So how do we determine forensic identification information? We look for fingerprints. Each hydrocarbon type has a different characteristic elution pattern, and based on this pattern, the type of fuel can be determined. We compare the sample from the environment to known fuel to see what it matches. Sometimes the sample is contaminated with naturally occurring hydrocarbons. This can cause results to be over guidelines and cause certain clients to think they need to remediate more than they actually do. And here's an example of different.
Anthony, sorry to interrupt. We might. Oh, there we go. We're having a technical issue, but I think the slides are up now.
They were?
Yeah, there are now. Okay.
Okay. I've only gone. It's okay. There's a chromatogram example of different hydrocarbons, such as fuel, oils, bitumens, hydraulic fuels, and a condensate. And there's some more examples of different fuels and hydrocarbons. We got gasoline, motor oil, aviation gasoline, jet fuel, diesel, and then an unknown. And when you compare the unknown to all these other standards, other samples, you can see that the unknown is a fresh gasoline. They match almost identically. So there are two main methods for analysis in environmental forensics: GCFID, which is common and primarily used for hydrocarbons. They're usually quick runs, and it provides enough information to identify product type. The fine details and contamination of biogenics is not easily determined. And this is what a common GCFID chromatogram would look like. It's a large, unresolved, complex mixture with peaks on the top, and it's hard to say exactly what any of that is. And then we also have a GCMS, where molecules are ionized and broken into fragments. These are then detected based on the mass to charge ratio. It's useful for compound identification and can determine the presence of biogenic compounds, but this requires training and interpretation and knowledge of the important ions to be able to look for it, to figure out what is biogenic and what is not. And there's an example of what a mass spectrum would look like with all the different peaks at different ion with using different ions. And then there is our 2D GC that we use over at Labs, which does these it separates even better. So the advantage of the 2D GC is going from this old 1950 Chevrolet to this super fast, cool Lamborghini. It's much higher tech, much faster, and much cooler looking. So what are the principles behind 2D GC? Well, there are two columns, one long, one short. The long one is about 30 meters, and the short one is about 5-ish meters. There's a modulator. This quickly traps, then injects the sample onto the second. Quickly traps LUN from the first column, and then quickly injects it onto the second column. This gives rise to a modulation cycle, which continuously collects small fractions of the effluent from the first dimension, ensuring the separation is attained, and then focuses it into a narrow band and quickly transfers this effluent as a narrow pulse. There are two main types of modulators: a thermomodulator, which modulates based on pressure, and a flow modulator, which is shown here, which we use over at AGAT, which the effluent from the first column fills the column loop. It traps it briefly, and then the flow back pressures and pushes it through very quickly onto the second column, maintaining the separation from the first column onto the second column. And there are many different kinds of detectors. There's an FID, there's time of flight MS, there's microelectron capture. As I mentioned, over at AGAT, we have FID detectors and time of flight mass spec on our 2D GCs. The benefits of 2D GC: it's multidimensional. It's better separation of co-eluting compounds and better specificity for compounds. There's less ambiguous interpretation. There's a greater peak capacity than one-dimensional GC. And it separates based on two properties, polarity and mass, compared to the 1D GC, which separates just based on usually polarity. And it gives a fuller picture with a better product and structure identification, and it just looks better. As can be seen with this very good example, you have this big mess of colors and shapes. With a 1D GC, it just separates based on size, but on the 2D GC, you can separate it by both based on size and color, and that gives even better separation than what the 1D GC provides. So the 2D GCs at AGAT, we have a 2D GC FID, which is used for a broad range of compounds, all the way from C6 up to C50, and for pHs. This is the primary instrument for the biogenic versus petrogenic analysis. And then we also have the 2D GC time of flight mass spec. It also has an FID detector, but this is used for light compounds, primarily condensates and light fuels. The range is usually from about C5 to C35, and it's our primary instrument for compound fingerprinting, with over 200 compounds mapped and more added as they get discovered where they are on the instrument. So the uses for the 2DGC, we currently offer product identification and characterization with sites with a mixed input, such as diesel, gasoline, or condensate. The better separation, we can see the separation of the products better and can determine what makes up a specific sample. The source identification and characterization, with better separation, we can better see differences between samples and see markers that are specific to certain companies, clients, or oils, depending on what is mixed together. Compound fingerprinting, where we identify specific compounds that are required by the client. Ecotoxicity, where we look at how toxic certain compounds are in the environment. And the F2 to F4 biogenic analysis, which is the new big thing that we're working on with the 2DGC FID. The old 1D output, you have something like this, which is a big mess, big unresolved complex mixture with some peaks on the top. It's hard to tell exactly what anything is, what peaks are what even is the sample, what the hydrocarbons are in it, what you can't say much about it. And then you go from this to the 2D output, which this is the same standard sample run on the 2D. And you can see how it separates better. You have the alkanes at the bottom, cycloalkanes right above it, biomarkers off to the side, alkobenzenes, naphthalenes, and it just goes up with increasing size of the PAHs here, the polyaromatic hydrocarbons, up to the chrysines, and it's not shown here because it would be hard to see, but it can go all the way up to the indinos and heavy and benzo A-anthracenes and AH-anthracene that are the really heavy ones that are up here. And we can also provide it, that was a 2D output, we can also provide it with a 3D output where it's the same material, but it's just shown in a different way. So again, we have the C10 to C32 with the aliphatics on the bottom. The biogenic region is indicated, and then again, the pH is separated up and up and up, all the way up to the top. So we can either do it in 3D, as I stated, or in 2D. We can analyze with either, and we can also analyze by groupings, such as benzenes, naphthalenes, phenanthanes, any of the polyaromatic hydrocarbons up, or we can do it using individual compounds, depending on what exactly the client is interested in looking for. So we do this by using what we call stencils. We have two examples here. So these can be drawn directly on the chromatogram in the program, and they can be used for any grouping of interest. So what we have here is an F2 to F4 stencil. So F2 would be C10 to C16, F3 C16 to C32, and then F4 C30, sorry, C16 to C34. And then we also have an aliphatic aromatic stencil, which is separated both out with the aromatics on top and the aliphatics on the bottom, and then it's separated into subgroupings like C8 to C10, C10 to C12, C12 to C16, and so on. And we also have the aromatics separated in the same divisions all the way up. This is more generally what it's used for because it's easier to draw the stencils for groupings, but they can also be used for specific compounds if they're required. So the analysis, we then, once the stencil has been drawn, we then integrate. And then this is what the integration output will look like. Each of those little peaks, X peaks, X is a peak. And then from that, we can just click a button and generate what's called a group type analysis report. This gives the areas for each of the groups in the stencil you've drawn. And from that areas, you can then calculate anything you would want. You can calculate concentration, or you can calculate percent of the whole of all the hydrocarbon material, depending on what exactly the client is interested in. So that gets us to our biogenic analysis. There are two main types of hydrocarbons we're interested in. Non-biogenic, which would be petrogenic or anthropogenic. This is of petroleum oil origin, oil, gasoline, or diesel. And then there's biogenic. These are naturally occurring hydrocarbons, which are mostly in the F3 region, but there are some F4 compounds. So like this PD area. And these can cause regulatory exceedances. If the total organic content is greater than 28%, it's an F3 exceedance. And the total organic content for certain peats, and some peats we have received at the lab, is greater than 40%. So already it's an exceedance, and it's all purely just biogenic material. And that's not good if you don't need to remediate the area. So there are some methods currently to separate petrogenic and biogenic material. The silica gel cleanup, this removes the polar organic compounds, which biogenic compounds tend to be, but it can be overloaded and saturated, and can be used with the 2D, though it's not as good as our new method. There's background subtraction, which removes background interference from the underlying environment, but samples can be heterogeneous, so you might not be subtracting exactly what the background material is. There's biomarker analysis, which looks for specific compounds known to be biogenic, but this requires training and interpretation and can be used on the 2B, but really needs an MS to do it. And then there's the BIC, or the biogenic interference calculation, and it's useful for determining false positives, but it cannot be used with heavy products or samples with a high water content. And then there's the GC or 2D GC biogenic analysis. The new method to separate the biogenic and petrogenic material and quantify them separately. It's applicable to all sample types, heavy product, and high water content, so there's no restrictions on it. So a brief overview of the silica gel cleanup. It's useful for the removal of biogenic compounds if a clean sample is required. However, it's not selective for only biogenic compounds, just more polar compounds. As most biogenic compounds are polar, it's very useful, but it can also remove some petrogenic compounds if they're sufficiently polar, i.e. alcohols, acids, and esters. And it can leave behind non-polar biogenic compounds, such as certain plant waxes. So it's good to an extent, but it's not the be-all and end-all. So here's an example of the silica gel on the 2DGC. So the polarity increases as you go up, and you have the before and after. You see the area of biogenic and the after. Some compounds have been removed, but not an extended amount. It is noticeable, but it isn't dramatic, and therefore there's still some biogenic material there, and it can still cause the overall result to be higher than the regulatory restrictions, and therefore it would still give a false positive. So in a 1D output with biogenic material, the chromatogram features are not well defined. It's not easily quantifiable. You need an MS to determine a specific compound. And it looks like this big, unresolved complex mixture with no definition, no definitive peaks or anything. The biogenic region is circled, but there's biogenic and petrogenic compounds mixed together. So it'll be hard to determine what exactly is biogenic and what exactly is petrogenic. So with the 2D GC biogenic analysis, we're using stencils. The method is able to partition off the different regions of the sample as petrogenic or biogenic. And once a stencil has been applied, the data is integrated and the group type analysis report, as I said, generated with areas for each region. The results can be either reported in a percent of the total, such as an area percent, or as a concentration, depending how the client wants it shown. And this method is fully validated in soil for the CCME PHC method. Excuse me. And here's what a stencil of the 2D of the biogenic region would look like. This is based off an F2 to F4 stencil. So we have the F2 region, the F3 region, and the F4 region. And then we have the biogenic F3 with this triangle here. And then we have the biogenic F4 with, as I like to call it, the upside down triangle on the other side of the line. And based on how the stencil is drawn, it only counts each compound once. it doesn't double count it. So each region has been drawn specifically for that area. And we can also present it in 3D form with the biogenic region being right up there circled. And with the 3D image, it shows very nicely how the biogenic area separates out from the petrogenic, aliphatic, aromatic area. So we've gone from this to this, where it's separated out very well from all the petrogenic material. You can tell what it is. You can determine specific compounds if you wanted to. You can see that it's separate and from all the other material, and it's its own distinct thing. So the benefits of this, it's quick. It takes about an hour per sample for calculations. The software can handle the intense integrations required. The software is intuitive and user-friendly. The 3D plotting, which I've just shown, makes explanations to clients simpler. And there's minimal overlap between the regions, less than 10%. This means it will not overestimate the PHC and will not report false negatives at all. And any sample above guidelines can be analyzed. It doesn't have to be something with a mid-range fuel in it or a specific water content. So, and then we'll compare it to this method to the BIC, or the biogenic interference calculation. So this new biogenic method works for all product types, including heavy fuel oils. It's applicable regardless of moisture content. No direct calculations. There is some minimal overlap between areas. There are no conditions for use. It is quantitative, and it can be extended to use in other matrices. For the biogenic interference calculation, or the BIC, it's limited to mid-range fuels, not applicable to heavier hydrocarbon products such as lubricating oils or heavier diesel fuels. Not to be used for high moisture samples. Calculations are required. There's a formula for it. There is no noted overlap, which it's one small benefit over the biogenic, but strict conditions must be met before application. It's semi-quantitative compared to the quantitative of the biogenic, and it's only applicable to soil samples compared to the biogenic, where we can use it on any material of interest. So here's some early performance data for our analysis of it. This is the percent recoveries of high organic content peat soil spiked with a heavy oil. And for the low and mid-level spike, it's all slightly over 100% recovery. While for the high-level spike, it's around 100% again, with only the F4 being a bit low. And then in the F3 and F3A and F3B, again, it's all around 100% recovery. So that's quite good. So the initial testing is positive, indicating that the biogenic petrogenic contributions can be separated and differentiated. So now I'll get into briefly some project examples of some samples we've gotten in from clients and analyzed. So this is an example of a low biogenic content sample. This was a waste sample. They wanted to know the percentage biogenic for disposal purposes. We determined that the biogenic area, which is indicated there, was around 1.5%, maybe even possibly a bit lower. So the disposal of the petrogenic material by the client was still required. But it's good that they knew that, and that they knew they had to continue disposal of the whole sample. So then this is an example of a sample with high biogenic content. This was a sediment sample. Previous analysis the client had done showed high response in the F3, F4 regions, and they wanted to know the true nature of what the sample was. We determined that it was over 90% biogenic, and therefore, when we determined that, this reduced the concentrations in the F3, F4 regions below guidelines, so they did not need to remediate the area before they continued on with their excavation and work in that area. And again, there's the biogenic region, showing that there's a lot of content there, and that's why the biogenic, the percentage of the biogenic was so high. And here's the final example. It was a mixed biogenic and petrogenic content. Again, this was a soil sample, and previous analysis again showed high response in the F3 to F4 regions. Again, the client wanted to know the true nature of the sample and what exactly they had on their property. We determined that it was about 15% biogenic, as can be shown there. There's material there, but it's much less of the whole compared to what all the petrogenic area is. So remediation of the petrogenic material was still required, and the client had to figure out where exactly this petrogenic material had come from, because it wasn't anything they had used in their work. So they had to go figure out where exactly it was from. So why use this method? It can help clients cut costs on remediation if they find out they don't need to remediate a specific area. It can be used in legal cases where disputes over impacts occur. It reduces human errors in estimating biogenic content, which can be the case with the BIC. And there's no restrictions on sample type or makeup, so it can be any kind of sample: soil, sediment, water, waste, whatever. And it can be any kind of water content or any kind of material in it. And it can be used for any kind of petroleum contamination, anything from gasoline up to heavy lubricating oils. So future work, we want to extend this method to more difficult contaminants and matrix types. We want to compare the method directly quantitatively to BIC and other approaches. And we would like to validate the method in other matrices that arise, such as mainly water to start with, but anything else that arises. We are proceeding with accreditation, but as written in the CCME guidelines, alternate methods may be acceptable where there is supporting rationale for such methods, which we believe there is for this. And clients have successfully submitted our results to get closure or approved risk management plans. I believe that's it. Any questions from anybody?
Thank you, Anthony. Sorry, everyone, about the little technical glitch at the beginning. If anyone has any questions, please type them in the question box, and we'll get to them.
Where's the chat?
Or the chat. Anthony, what's the uptake been like with your clients? Are they using this?
Yeah, they are. I had a sample in. I've had a couple samples in the past month or two to look into this, and I believe it's getting around, getting known that it's out there.
Okay. What are the sampling requirements for the 2D GC?
Same as any 1D, standard soil sample. I think what we use a 125 ml jar, I think, fill. There's no differing sampling requirements from other analysis methods.
Okay. And then give me 1 second here. What's the difference in cost between the biogenic and the BIC?
I believe it's a bit higher. We don't do the BIC at our lab, so I'm not sure what the price is at.
Okay.
What the book price is on it. The price of this is competitive with other ones. I believe it's $450 or something like that. I can't remember the exact price on it, but I don't know the exact price of what people charge for the BIC, so I can't say.
Okay. We've got another one here. Is methanol field preservation required?
No, but if you want to, you can.
Okay. Just for everyone, copies of the presentations are available on the ESA website, on the RemTech website, under the agenda page, proceedings. You'll find all the proceedings from RemTech 2021, and you'll find these and all the other presentations available there. And there'll also be a video recording of this that'll be available after that. I will send out to everyone. So Anthony, there's no more questions with that one. So thank you again. Thank you, Agate. And we'll now go to our next presentation.
Stop.
Our
Thank you.
next presenter is Joe Ricker with EarthCon Consultants.
Hello all.
And
Hey,
morning,
Joe.
Joe. And Joe's going to be speaking to us on groundwater plume analytics tools for environmental site assessments. So if you could just bring up your presentation.
What? I have it on, but I don't. I've got two screens, and I can't tell with webinar which screen it's showing.
It's there now. So if you can put it in the
Okay.
presentation mode.
Yeah, that's okay. Shoot.
Okay.
How do you switch screens? Because it won't let me do it. Make another.
You're,
Yeah, usually it asks you which screen you want to share, and it's only going up on the other screen.
yeah, well, you're almost there.
Oh yeah, I
Slide.
know no, I know it's putting it on the other screen is my problem. It's
Oh,
putting it on my second screen. What if I just undo it? There it'll go. I'll just undo that screen. Okay.
okay. You're good.
That'll work. Okay.
I'll be back for questions at the end. Thank you.
Okay. Sounds good. I will get it going. Thank you. So I'm going to talk about, again, just reproduce the presentation I did at the RemTech. And so I'll jump into this and there's going. Okay. So I'm talking groundwater plume analytics. And using the term analytics, you can see the definition here. I'm just going to give a quick definition. You can read it. But the idea is taking, groundwater data, the complex data we collect at contaminated sites, and then using those data in a meaningful way to communicate insight. That's really the crux of what we're doing with plume analytics. And so I'll show you a couple examples of that. Before I do that, real quick, some of the benefits of using these tools. Just real quick on my background, I came out of the chemical manufacturing industry many years ago, and we were faced with very large Superfund remediation sites and trying to understand plume behavior when really the state of the practice then, in a lot of cases, even as it is today, is doing well by well trend analysis. And it's hard when you have, 50, 100 wells at a site. Some wells are increasing, some are decreasing. How do we look at the overall, plume behavior? So that's what these tools were born out of and been revised over the years, but I'll show you an example of those in a minute. But here are some of the benefits of doing that. Obviously, project management, understanding plume behavior is very important from that standpoint. A lot of our sites we're operating remediation systems. We're really good in our industry at knowing when to turn systems on and get them going. Sometimes we're not quite as good, I think, I've noticed, at knowing when to turn them off. And so these tools were designed to help evaluate, plume data, groundwater data, with respect to turning active remediation systems off, demonstrating natural attenuation. We really want to show, and these tools will be very apparent here momentarily, showing natural attenuation, biodegradation, stable trends in plume mass, things of that nature. Back to remediation systems, we do have them in place, and sometimes we just want to monitor what the effect of remediation is. So if we have, say, for example, a pump and treat system, a lot of times we're evaluating those systems based on what I call the above ground metrics, like mass recovered, maybe energy efficiency, all those things that are more above ground. But what we're going to do is marry that with what's the subsurface doing, what's the plume behavior in response to remediation. So we'll look at some examples of that. Optimization of groundwater systems. I'll show an example of what we call well sufficiency analysis, trying to understand how can we reduce a monitoring well network, but still maintain the integrity of the network and its ability to evaluate progress of remediation. Attenuation rates, that's more for chlorinated sites. Probably won't get into that here today, but and then litigation support, I'll do a small example of that as well. So what I'm going to do is go through the baseline or the platform of our plume analytics tools, and that's the Ricker method plume stability analysis. And that is a method I developed years ago, like I said, back in industry. It's been published, and a lot of our tools are going to be based off of that. And then I'm going to show you spatial change indicator analysis. That's another one of the tools we use to evaluate plume behavior. And then we'll look at well sufficiency analysis. Like I said, that's one of the optimization tools we use. I will highlight these using examples for sites. So the first one I'll look at is a chemical plant in Southern Ontario. We'll look at a bulk terminal facility in Northern California. And then I'll show you just a quick example of a commingled VOC plume, chlorinated VOC plume, that I was an expert witness for litigation. So we'll walk into those and explain how these tools work. This is the Ricker method plume stability analysis. It is published. peer-reviewed and all that. If anybody wants a copy of that paper, it's in the public domain, freely available. A lot of folks are using it. That is available. I can get that to you if you can't find it online somewhere. So the first example was an active chemical plant in Southern Ontario. They made a wide range of chemicals, including mostly herbicides, a lot of byproducts in that process. So what I'm going to do is focus on this first one, NDMA, the N-nitrosodimethylamine plume, and it's a very large plume. So this is an entire village here, and this is the plant site in green here, and you can see the plume goes off to the southwest here. And so the Ricker method, what we're doing is looking at metrics of the plume. So you can see on the bottom, we have the area, the areal extent in hectares, and then the average concentration, which is a spatial integration across the plume. And then we have the plume mass indicator, which is a combination of these first two, or mass estimate. The yellow cross in the middle is the center of mass. So this is the plume as it existed in 1993. And so what we can do is look at every plume map. This is an empirical analysis of data through time. So what I'm showing you now is here are the data for this site for the last 25 or so years. You can see how that plume has behaved, and you can see what's going on. I'll play that again. So I'll play it again just for reference here. You can see the red wells are extraction wells, and you can see the effect of those wells. There's a big extraction well down here as well, but you can see how the plume is behaving, how it's getting smaller through time, and just a really strong way to show what's going on for plume behavior, and you can see it and understand it. I want to stress here, it's not a model. We're not calibrating to site conditions. This is empirical evaluation of real data. That's it, looking backwards using existing data and creating these maps, stitching them together in a video. So you can see the behavior, but we can now look at more objective metrics. So the first metric we'll look at is the areal extent, and you can see it is decreasing statistically using Mankindle and regression, very strong confidence in these decreasing trend. Now you can see since they started pumping in 1998 through 2019, that's about a 40% reduction in plume area. And that was the only metric they were using. So when I came into the project a few years ago, the only metric that was being used to evaluate progress of remediation was area. And so this is about a 40% reduction in area, and that's all fine and good. But they were really wanting more. So when you look at average concentration and mass, you see much more significant decrease. We have more than a 99% decrease in plume mass. And you can see within that plume, just a whole lot of decrease in the mass. Again, very strong decreasing trends. So now from a plume stability standpoint, where we can show you objectively that these are in fact very strong decreasing trends in plume area concentration and mass. So the next thing we can do for these sites is look at the center of mass. How is the center of mass behaving? And so what I'm showing you are all the centers of mass plotted on a single site map, and they're color coded. So the earlier years are darker blue, the more recent years are the lighter blue. And we can just get a sense of the relative movement of center of mass through time. And look at the zoomed in chart up here. You can just follow the colors and get a sense of where the center of mass is migrating. It's really all over the place. So if you can imagine center of mass at one location, at the next event at a different location, connect those two events with an arrow, and mathematically that's a vector, and we can plot those vector movements, and that's what we're doing here. So anchoring them at a common point and looking at all the different movements of the center of mass, and you can see it's all over the place. And that's actually a very strong, stable signature. For example, if you had a plume that was increasing, that center of mass would tend to move in a down gradient direction, and that way the movements are always in the same direction, and the pattern would be these vectors would all line up in a single quadrant. And that's an indication of an advancing plume. And so we don't see that here. We see them all over the place. You see the net movement is really about 10 meters to the west, just a very little net movement in center of mass. Again, a very strong, stable signature. So that clearly is the case with this site. And the next thing we do, the last thing we do for every one of these projects is look at what we call the spatial change indicator. So for this analysis, we're going to look at spatial changes through time. And so for every event, we're going to compare it to the first event. So 93 is in this top left. That's our baseline plume. The next event is the 94 plume, and we're going to essentially subtract them from each other and look at spatial differences between them. Anywhere concentrations decrease, it shows up over here as blue. So on this resultant plume as blue. The darker the color, the more the decrease. Anywhere the concentrations increase, it shows up over here as red. or the darker the colors indicates more increase. So this is qualitative. It lets you see through time. I'll animate this in a moment, spatially where mass is going in the subsurface. And we can look at that through time, like I said, very qualitatively. On the bottom, we can look at the amount of change in area, concentration, and mass on a percent basis. And then we can also look at the magnitude of change. All of the red is an increase. We can quantify that. All of the blue is a decrease, and we can quantify that. So just a tremendous amount of information on this single graphic. One thing I want to point out here, E7, E9 is an extraction well, and you'll notice some patterns with that well. It was a former municipal supply well, and it was actually pulling this plume to the south. So when we animate this, you can see the effect of W3 big extraction well here. Lots of blue is building around this well, lots of decreases throughout the core of the plume. And even better, we see this darkest blue, which indicates 100% decrease, and you see the plume no longer exists. The footprint, the aerial extent has come in a little bit, but we see lots of decrease along the periphery. Just a tremendous amount of decrease we can see in this plume, and that's very good when demonstrating behavior, of remediation at this site. And you can see it's about a 48% decrease in aerial extent, but we see 99% decrease in plume mass. And this does illustrate another point, by the way. Very common phenomenon we see at a lot of plumes and a lot of sites where people are evaluating plume behavior just looking at the footprint or the aerial extent. But the footprint rarely describes what's going on throughout the plume. And here's a case in point. We see about a 48% decrease in area, but a 99% decrease in mass. So it rarely can describe what's going on in the core of the plume, especially for older, mature, advanced plumes that that's been there for a long time. And what's happening on the periphery is going to pretty much be it just doesn't change much. But what goes on inside the plume can be very, very significant. So we see that here. You can see the effect of E79 is kind of the remnant here. The plume is decreasing, but when that well was operational, it was actually pulling this plume to the south. So we were able to use this, and I'm not going into the details of this, but we were able to turn that well off actually by using this analysis. So at the end of the day, we were able to turn off ceased operation at E7, E9, and really were able to get a better understanding of remediation progress and what's going on at the site. And one of the best benefits, I think, of this was with the stakeholders. So for this particular site, there were 3 active community groups, and it was pretty contentious, actually. So being able to show this in a public meeting and let them see what's going on brought a lot of comfort, and a lot of to the community around the site and all the community active groups on what was going on and understanding in a very easy to see way. So that's what analytics is, taking all of these data and presenting them in a way that makes it easy to see. So what I'll do is I'll use a different site, different example to illustrate these tools a little bit further. So this is an active bulk terminal. It's in Northern California. It's actually 3 sites in one. So there's one bulk terminal with 14 large ASTs, a second one with 6 above ground storage tanks, and then a former gasoline site, all in one big commingled plume. And so a lot of BTEX, TPH, but we're going to look at just the benzene plume for this site. So this is the benzene plume. The blue wells is one terminal. The red wells is a second terminal. And there's another retail site that will come in down here, some other wells you'll see. So when I animate this, real similar, same procedure, but you can see we're looking at the benzene plume behavior. You see those black wells come in. So a lot of those wells are being added to the system as we go. You'll notice also lots of gray wells are coming in. These are remediation wells, pumping wells over here, some SVE wells come in up here, air sparging wells, a bunch of dual phase extraction wells come in here. So you can see as time goes on, these remediation wells get installed, and you can see the effect on the plume. You can see that it's shrinking through time, and we can track and visualize the progress. At this site, there's over 90 plume maps, and I was able to show you pretty much the plume behavior in 30 seconds of what's going on at that site. So again, these tools are great for evaluating behavior progress and showing it, demonstrating it, getting our regulators on board with it of what's going on, understanding site behavior. So for this site, looking at the trends, they had a major expansion in 2001 and then started a lot of remediation efforts in 2003. And you can see very strong decreasing trends. Again, notice the area doesn't decrease substantially. In fact, since 2010, the area really hasn't changed a whole lot, but a continual, very strong decrease in plume mass. You can see the plume mass statistically, very strong confidence, decreasing trends in all three of these metrics. Really strong way to show what's going on at this particular site. In fact, I'll talk more about this in a moment. When the more or the better we understand plume behavior, the more decisions the regulator can make on what to do next when we have a good understanding of how a plume is behaving. So again, center of mass for this site, groundwater flow at this site is actually to the west. And you can see just a gradual migration to the east of the center of mass, just a very strong up gradient shift in the center of mass. Again, very strong, stable signature there for the center of mass for this site. So back to the spatial change indicator for this site, we'll evaluate this as well from just that 2001 baseline event, comparing back to it. Now, when I play this, you'll notice we have some red areas. This is where the tank farm is. A lot, some sourcing going on in the early data. But then eventually, as these remediation wells come in, you'll see this red begin to diminish and turn more blue, indicating more remedial progress in here. Lots of really dark blue throughout the core, especially along this line of dual phase extraction wells, air sparging wells up here. We see the effect around these remediation systems. And again, we see this very strong decrease along the periphery of the plume. And similar to my last example, 41% decrease in area, but a 94% decrease in mass. Just a really strong way to show remedial progress at this site. In fact, we're able to do even more with it. So with this site, we also did well sufficiency analysis. So with this, same exact plume, same behavior, nothing new there. I'm just going to advance that to the end. Here are the trends for all of the data for the site. And we're going to focus on the last 5 years. We're going to optimize this network now. We're going to remove some wells and look at just the behavior in the last 5 years. So if I zoom in on that, here's the trend behavior, the area concentration mass with all wells that are in the network. So what we do is a quasi-professional judgment approach and remove wells from the network. These wells in purple will have all been removed as if they never existed. We simply rerun the analysis and then show, it's hard to see visually, but we can compare more objectively here. These are the trends with all wells in the network. The orange lines are the trends with 14 wells removed. That's a significant reduction in the well network, significant cost savings, but you'll notice our conclusions are the same, our interpretations are the same. We haven't really lost anything here. And we can, this is really, really good. So we look at comparisons. The trend with all wells and the trends with the reduced network should match. We also look at the relative percent difference of every pair on here, get the average RPD, and then we look at the correlation that they should be in lockstep. They should follow the same pattern. And all of these look really, really good. So what we do is we continue the process. We actually ended this site with 27 wells removed. All the wells in purple have been removed. And again, we just redo the analysis as if they never existed and get the results from that. So again, trends with all wells in the network, 27 wells removed. This was the final product. This was presented to California on the Water Board, and this was approved. So a 40% reduction in the network. And then because of the understanding of behavior, we also achieved a reduction of frequency from semi-annual to annual. So just a significant reduction at this site. That's the current network as it was prior to optimization. That was the network after optimization. You can there's still sufficient coverage, but we have a 70% plus cost savings for O&M for that site based on that. I got ahead of myself here, but again, better understanding of remediation. We turned off 2 of the 4 remediation systems at the site using this analysis. And then also the well sufficiency, you can see 40% reduction in wells, 50% reduction in frequency for a net, 71% reduction in monitoring costs at that site. Just a very strong way to do that. So the last example I want to show you is from a litigation project I did where it was a former machine shop, and that was my client actually, was a machine shop that operated in the 60s. And so this was a furniture mart, or it was a retail site, and they had done some ESAs and found a chlorinated solvent plume at the site. And of course, they're going to find out through the title history, who may have done that. Well, they came across our information in the 60s, from a machine shop. Now, it was other things since then. It was a printing shop. It was other things that could have caused some of the contamination, but they're really pointing it back to my client in the 60s. And so lots of chlorinated ethenes and ethanes. And so what I'm going to show you is a cool way to look at some chlorinated data using molar ratio analysis, molar fractions. So here's the total chloroethene plume. Let me jump back. This is the building that's on the property. Okay, so lo and behold, they find this plume. Here's a total chloroethene plume. Just note we are in molar, nanomoles per liter, just total molar basis plume here. And it's interesting if we look at the data. So for each of these points, based on the most recent sampling event, look at the molar fraction. So the PC is the dark red, TC trichloroethene is the pink, cis-1,2-DC is the dark blue, and vinyl chloride in the light blue. And we're looking for patterns now. One thing you'll notice, if this was a building that my client operated in the 60s, about in this area, notice what we see, this first pattern. This looks like a degraded TCE source. So there was a TCE source, and that, by the way, is the contaminant my client would have used. It's pretty degraded, it's fractionated. We can see it's broken down to DCE and vinyl chloride, and you can see that it's likely contributing to this plume on some level. But notice the total molar concentration of about 3,000 nanomoles per liter. We see this looks totally different, off-site, down gradient, much higher concentration, and the patterns are very, very different. This looks like a newer, younger release of TCE at a higher level. And so the first thought is, you know what, there's no way that this could have caused all this down here. The patterns don't match. We have some area of commingling in between. And even more than that, look at the chloroethane data. So here's chloroethanes, and look at the molar fractions here. In the area where my client operated, there's nothing. It's all non-detect. But again, we see TCA, 1,1 TCA, 1,1 DCA, and 1,1 DCE degraded. Looks like a young release again of TCA, and look where it's located, down gradient off-site. So, this is, again, starting to come together here that, wow, this probably isn't from my site or from the client. It's probably somebody else causing this. And if that wasn't enough, we come to the chloromethanes. Again, carbon tetrachloride and chloroform, we only see it in this area. So at the end of the day, and there was so much more to this, don't get me wrong, but we were able to excise, if you will, just a very small piece of this plume that's contributable or attributable to my client up here. In fact, more investigation turns out if I overlay all the plumes on top of each other, there's a commonality between them. Turns out this was a release from a sewer, a storm sewer that drains an area along this street out here that's a very industrial area, and there was a break that had caused a lot of this contamination, and that's what it was attributed to. But all of that was stemmed from simply looking at the data and being able to see very clearly that what we see in this big plume that was out here could not have come from a small source up here. It must have come from somewhere else. So just again, using those tools to do that, and that's everything I've got to show. So I'm right at 22 minutes. So I appreciate it. A lot more with this. If you have any questions, please email, call. Very happy to follow up, show you more examples, and see how they could work. So Joe, back to you. I appreciate the opportunity.
Thanks, Joe. Really appreciate that. Lots of information there. If anyone has any questions, please type them in the chat or in the questions box, and I'll get to them. Just give everyone a second to type if there's any questions. Joe, where are you located out of?
I'm actually in Memphis, Tennessee. And it was nice to get to the mountains. We don't have mountains around here.
No.
You have to go to East Tennessee for that.
Yeah, but you still got pretty country down there, so.
Yeah, it is nice.
Okay, I don't see any questions, so feel free to reach out to Joe if you have questions directly. And as I said again, the presentations are available online. Oh wait, can you comment on the N alkaline weathering for samples closer to the source than further removed from the source?
Say that again. I didn't quite get what.
Can you comment on the N-alkaline weathering for samples closer to the source than further removed from the source?
We did not do isotopic analysis, if that's what you're asking. It was more, let me get that out of the way. Talk on it. Hold on, I hit the wrong button here. I'm trying to minimize this off my window. I can't do it. All right. I'm not sure what the question is asking. I was trying to read it. So, but if I understand, you're asking if we did like fingerprint analysis or looking at signatures. I guess I'm trying to understand what the question was. But we did. All we're looking at is fractions or molar fractions within the actual data set itself. So I don't know if I could.
Okay. Dee, why don't you reach out directly to Joe and he can answer your question.
Absolutely, yes, yeah.
You said want to know about N-alkane distribution.
Let me pull it back up.
Want
Distribution.
to know about N-alkane distribution.
So this is because it's a litigation project. I'm not showing a lot of the specific information for it, and I've just done it on a total chloroethanes and chloroethanes and chloromethanes. I broke them out individually into contaminant class. So if that's, but I can probably go more into this if you want to, contact me offline. I can give you some more information on what we're doing with that.
Yeah, Dee, just contact Joe offline. That'd be great.
Yeah.
So thanks again, Joe, for presenting. Really appreciate this, and we'll move on to our next presenter.
Thank you.
You're welcome. Our next presenter is Brant Smith with Evonik. Brant's bringing up his presentation. Brant's going to be speaking to us today on enhanced in situ solidification and stabilization blends, impacts of adding sodium persulfate and water content. Brad, if you're there, you bring up your presentation, that'd be great. Perfect. Over to you.
Just getting there. Okay, great. Thanks, everyone. Thanks for the opportunity to present with you again. My name is Brant Smith. I'm the Director of Technology at Evonik Active Oxygens. I'm going to be talking to you today about enhanced in situ solidification and stabilization blends, the impacts of adding persulfate and water content. One of the first things I wanted to say is some of you may not be familiar with Evonik Active Oxygens or Evonik Soil and Groundwater Remediation. We were formerly FMC and Adventus even before that. So Adventus was purchased by FMC, and then all of that was divested to form PeroxyChem. And then as of October, it actually happened while we were in Banff. Evonik made the official transition from PeroxyChem to Evonik Active Oxygens. So going forward, what had been PeroxyChem is going to be known as Evonik Active Oxygens. So today I'm going to be talking to you about the technologies that we are talking about, the in situ chemical oxidation and in situ solidification and stabilization, why we would combine those technologies, different things we can do with the experimental design on how to make these work and testing things out, the results from a series of studies that we did, and then of course a summary and conclusions. First, in situ solidification and stabilization is a technology where you're adding a series of binders, usually things like Portland cement, blast furnace slag, cement kiln dust, those types of compounds in with contaminated sediments. The goal is to stabilize those contaminants or solidify those contaminants. Those vary a little bit in that stabilization is a chemical process that will reduce the leachability. The easiest thing to think about here is some sort of metal compound that will form a metal hydroxide at the high pH that you get with Portland cement. As an actual precipitate hydroxide, it's going to be less soluble than it would be if it was in an aqueous phase. Solidification is much more of a physical process. This is where you are decreasing the surface area, decreasing the hydraulic conductivity, decreasing the effective porosity, increasing the compressive strength. So you're forming a nice solidified matrix that it's going to be more difficult to have significant contaminant flux from that matrix. In terms of remedial goals, quite often for ISS, people are trying to target something reducing the hydraulic conductivity by 2 to 3 orders of magnitude below the native soils. A common remedial goal is to get the hydraulic conductivity down to 1 times 10 to the negative 6. So again, this is a solidification type of goal. They often also target an unconfined compressive strength, or UCS, in the 20 to 60 PSI range, and it's very common that with ISS that they target 50 PSI. This isn't necessarily hardened. This is certainly not a concrete. If you think about a concrete, the pressure on a concrete, or the PSI on a concrete, is usually 3,000 to 4,000 PSI. And here we're talking about a couple orders of magnitude lower than that, with 20 to 60 PSI. I actually went back to my geotechnical book from college and pulled up this data, talking about how to compare the consistency of a soil to this PSI range, this unconfined compressive strength range. And really, the 20 to 60 PSI range that we typically target is consistent with a stiff to very stiff clay. Again, 20 to 60 PSI. This solidification, of course, lowers the contaminant flux and lowers the leachate concentration. In situ chemical oxidation is the other technology we're talking about here. It's a different type of technology in that it's really adding a bunch of thermodynamically powerful electron acceptors that can transform the organic contaminants of concern via an oxidative pathway, typically an oxidative pathway. So it's a destruction technology. So whereas with ISS, it's a solidification stabilization technology, the contaminant is still there. It's just less accessible. It's not going to have the same kind of groundwater flux, or it's not going to be fluxing out of a source zone down gradient as much. With ISCO, you're actually going in and destroying the contaminants of concern, at least the organic contaminants of concern. So getting a little bit more into the oxidant, talking about closure persulfate, there's really 2 types, sodium and potassium persulfate. The primary difference is the salt of each of these. The sodium is more highly soluble, the potassium is less soluble. They both dissolve to release the same persulfate anion. Sodium, just because of the higher solubility, the anion is there available pretty much upon the application, whereas potassium persulfate is a solid slurry that's injected and slowly dissolves over time. The persulfate anion is a strong oxidant and can be activated to form both the oxidative and the reductive pathway. Because you get both pathways, you basically can treat a very broad range of contaminants of concern. The persulfate anion tends to be stable in the subsurface for a period of weeks to months, whereas KP can sit there and slowly dissolve. Potassium persulfate can slowly dissolve. We've seen it persist for years. Because you get both the oxidative and the reductive pathway, like I was saying, you can treat a very wide range of different contaminants of concern. Important here is with alkaline activation, you get both the oxidative and the reductive pathway. So you can treat your carbon tetrachlorides, your TCAs, your DCAs, some of the compounds that Joe was just talking about in the previous presentation. You can also get your petroleum hydrocarbons, your MGP residuals, your oxygenates, 1,4-dioxane, those types of compounds that require the oxidative pathway. And then also, of course, there's a number of compounds that can be treated via either, most commonly PCE, TCE. Oxidatively, they tend to go by attacking the double bond. Reductively, they go via a dechlorination mechanism. But with alkaline activation of persulfate, you get both of these. So how can these compounds be combined? Very simply, the common ISS reagents act as alkaline activators of the persulfate. They actually play very nicely when you blend them together. Portland cement is a very strong alkali. Typically around 50% by weight of Portland cement is equivalent to calcium oxide or quicklime. That's a very alkali substance. Blast furnace slag is a mild alkali, but actually works very nicely when combined with Portland cement and persulfate. Cement kiln dust is another significant alkali that's commonly used. We would encourage you to be careful about high carbonate content because the carbonate can interfere with persulfate chemistry. So the bottom line is you can add and combine these reagents and you can get both pathways going. You can get the stabilization, solidification, and the contaminant destruction. But we also want to talk about a little bit more of, even if you don't want to add to get the contaminant destruction, we are seeing benefits of adding sodium persulfate to ISS. Even if your goals are just the compressive strength, a reduction of flux, reduction of hydraulic conductivity, there are some benefits to adding persulfate. So first, ISCO-ISS, the benefits of adding ISS to ISCO, it's very simple. Soil mixing allows you to get a lot of contaminant, a lot of oxidant into the site, your source zone, in a single application. The mobilization costs have been coming down. It's now getting to be quite cost competitive with injection strategies. So there's some serious benefit. Instead of needing 2, 3, 4 applications using an injection strategy, you can get all of that mass in a single application. But there is a little bit of a hang-up in that you have broken down the compressive strength or the cohesive strength of the soil by blending it all together and agitating it mechanically during the mixing. Well, here's the benefit of adding a little bit of ISS with ISCO. You can still have the remedial goals, the contaminant destruction, get all that chemical oxidant in there. But if you want to be able to work on the soil, drive onto the soil after the fact, you may want to add in some ISS reagents in order to have that compressive strength. Usually you can access a site within a few days, if not a week or so after the application, if you add the ISS. If you don't, it could be months or longer before you can actually physically access the surface of the site after a soil mixing application. But getting down to ISS only, you're not trying to destroy the contaminant. That's not part of your remedial goals. What is the benefit of adding sodium persulfate to ISS? Well, really there's 5. One, the contaminant destruction does reduce the long-term risk, because remember, ISS is non-destructive. It's an immobilization technology. So the contaminant is still there. Well, by adding ISCO, you get some destruction of that contamination. You get lower leachate concentrations. You get higher compressive soil strengths is what we're seeing. And also we're seeing that you get lower hydraulic conductivities. But by adding persulfate, by getting the higher compressive strength, the lower hydraulic conductivity, one of the things people are doing and seeing is you don't need to add as much reagent. You don't need to add as much binder. You don't need to add all that much persulfate. And by adding less reagent, you're getting less soil bulking. And this is a critical cost savings potentially, because if you're having significant soil bulking, 15, 20, 25% bulking, then you have to take that material and do something with it, either at the site or, if it's hazardous, as a hazardous disposal, which can be quite expensive. It's actually the less bulking. It's not using less binder that's going to pay for the persulfate. It's actually the lower and less bulking that can sometimes, at a few sites, has been sufficient enough to pay for the addition of the persulfate. So getting into these different mechanisms, contaminant destruction, this is an MGP site. This is actually taken from a journal article, Vipul Srivastava with Dan Cassidy there at Western Michigan. They published a series of articles. This is one of them, summarizing the data from one of them. It was a highly contaminated site. I actually don't know exactly how highly contaminated. The 36,900 milligrams per kilogram TPH was summarizing the BTEX, the naphthalene, and the 17 PAHs, but invariably there was probably some other total petroleum hydrocarbons there at the site other than those 3 analyses results. So highly contaminated. The sodium persulfate and Portland cement were added at a ratio of 1 weight sodium persulfate, 2 weight of Portland cement. So if you had 4% Portland cement, you had 2% sodium persulfate. And then generally, one of the things I really wanted to know is that the ISCO was underdosed. When you think about the amount of contaminations that's there, the ISCO was underdosed for the application, yet we saw significant contaminant reduction. So this is the contaminant destruction. You can see in the table or the figure there to the right. The BTEX, because it's, you saw preferential treatment based on solubility, the BTEX are more soluble. So we saw over 90% destruction of the BTEX. We saw over 80% destruction of the naphthalene, which is again fairly soluble. So you get preferential treatment over less soluble compounds. Speaking of less soluble, you can see the PAHs. you only got, marginal treatment of that, going up and approaching 30-35% reduction of the PAHs, but it's still contaminant destruction. It's still a reduction, especially when you can compare it to the dashed line that you see at the bottom, which is no contaminant destruction from the ISCO or the ISS only, without any of the ISCO. So the top here, so that's benefit number one. Benefit number two is lower leachate concentrations. The top figure that you see is actually also from that Srivastava et al. Article from 2016. And you can see that whereas the goal of ISS only is to reduce the leachate concentration, which results in a lower mass flux, and you can see that that happened. You see that, as you increase the binder up to 10%, you are getting somewhere around, 30 to 40, maybe up to 50% reduction in the leachate concentration of the different compounds. However, and that's the dashed lines, the solid lines are where you had ISCO combined in there with the ISS. At every single time point, you saw a greater reduction in the leachate concentration of the contaminants when you combined ISCO with the ISS. And it's very easy to understand. Less contaminant is there. There's less to desorb. There's less to go into the leachate. So you do see lower leachate concentrations. The bottom figure is from a field pilot study out of Brazil. And basically this shows for 8% binder Portland cement and 12% binder, as you increased incrementally the amount of sodium persulfate from about 0.25% up to about 1.6%, you saw decreasing leachate concentrations. With the 8% Portland cement, you went all the way from around 650 micrograms per liter, all the way down to less than, it actually ended up around 67. It was a full order of magnitude reduction in the leachate concentration. And this was actually a series of field pilot studies. They did a number of different cells. So this is an average of all of that data. So looking at across a significant data set, we saw a very consistent reduction as you increase the amount of closure SP in the system. So lower leachate concentrations by adding ISCO. So compressive strength. So the blue line, working with this figure, this is data generated at the Avonic Active Oxygens lab in New York. We ran a series. This is Portland cement blast furnace slag, again, 8%. And you can see no sodium persulfate added is the blue line. And every single time point, every single test condition, as you added the sodium persulfate, you actually had stronger compressive strength. And actually quite significantly stronger compressive strength when you look at it. One of the things that we also wanted to show and emphasize is that 8% binder, the Portland cement blast furnace slag with 2% sodium persulfate, was actually in the same vicinity as the 90-day time point for 15% binder only. So again, showing you that you can actually add less reagent, in this instance 10% by weight total reagent, and get the same compressive strength here, 15% binder by weight, by adding and combining the ISCO with the ISS. Looking at the same data, this is again data generated by our laboratory in a study that we were doing. I just wanted to provide some actual numbers and comparison. So 8% Portland cement with adding different amounts of sodium persulfate, you went from 90 psi at day 90 up to about 110 psi at again day 90, but with 2% sodium persulfate, or about a 22% gain in strength. But with the blast furnace slag, the Portland cement blast furnace slag combo, this was a 70-30 blend, 70% Portland cement, 30% blast furnace slag. It was Lafarge Alpina type 1-2 Portland cement. You actually saw a 60% gain in strength. You went from 110 psi with no sodium persulfate all the way up to 175 psi with the addition of persulfate. So a very significant gain in the actual strength compared by adding the sodium persulfate. In terms of lower hydraulic conductivities, this is going back to that field pilot test from Brazil. By adding more and more persulfate, again from 0% in this instance all the way up to 1.6% sodium persulfate, you can see by averaging together a number of the data from a number of different cells. As you increase the amount of sodium persulfate added, you also we're getting approximately an order of magnitude lower hydraulic conductivities. And in this instance, this is actually important because 1.1 times 10 to the negative 6 centimeters per second is a very common remedial goal. And you can see here by adding, and this was a combination of the 8% and the 12%, by adding binder only, we actually didn't achieve the remedial goals on average at the site. However, once you start adding over 1% sodium persulfate, you are getting below the remedial goal of 1 times 10 to the negative 6. So taking all of this phenomena, you get your contaminant destruction, you get lower leachate concentrations, you get greater compressive soil strength typically, lower hydraulic conductivity typically. You can basically get away by adding less reagent, which results in less soil bulking, which can be a very significant cost savings at a site, especially if you're having to dispose of that bulk soil at a hazardous waste facility. So I'm going to pivot a little bit. So that was all about the benefits of adding ISCO to an ISS application. And I'm going to talk to you about some observations we've been making about the importance of water content in all these studies. It's something that I think we often take for granted, but ISCO, ISS, and ISS, they work in vadose zone, which has a certain amount of moisture content. They work in saturated zone, which has a different moisture content. And we're seeing that water is a very important variable in this technology. So first point that I want to make is that even vadose zones have water. There's for the hydrogeologists out there and geologists out there, this is very known. I'm an engineer, but I did take these courses, and so I do have some recollection of it all. And I went back to my books and was pulling out the terms specific yield plus specific retention. It equals 100% of a pore volume. And basically, the specific yield is the percent of a pore volume that will drain by gravity. So if you just take a puck of soil and you have it completely pore filled, the specific yield is the percent of the water that's in that puck that will drain by gravity. The specific retention is the amount of that pore volume that is retained by the soils. And what's really interesting is it's pretty significant. With a clay, you're typically retaining about 98% of your water in the soils. The sandy clay is about 93%. A sand can be 73 to 79% of that moisture is actually retained in the soil. So you can have 75% of a pore volume in a vadose zone. So that's the first point with water. Vadose zones can have quite a bit of moisture in them. In a desert, of course, they may not. Or underneath a parking lot, they may not, because they haven't seen moisture in so long. But if you are going out to a nice field or something like that, you can be dealing with a good amount of moisture already out there in your soils. So talking about water and trying to make this make sense, this is a bit of a complicated table, and I do apologize for that. But one of the things that I've run across is that different people talk about water differently. Coming from an ISCO background, we tend to talk about pore volumes. Some people tend to talk about moisture content. Some ISS people talk about the ratio of water to the binder. So I'm just trying to take a second and show how this looks. If you were to go out with a vadose zone, for example, and you figured out that there was a moisture content, and moisture content can actually be based on dry weight of soil or wet weight of soil. But if you're basing your moisture content on dry weight of soil and you had 15% moisture, that's actually a sand, the specific retention that you see from a sand. That's 75% of a pore volume. The binder ratio of that would be 2.48. So this is a table that's intended, if you have some data, you go to a lab, you generate it. This is encouraging you. If you have a moisture content based on dry weight of soil of 10%, you have about a half a pore volume in there, using the assumptions that I have there in the notes, 110 pounds per cubic foot, 35% porosity, etc. Also want to know, this is what we tend to target, is because especially going into the saturated zone, you already have a full pore volume, and contractors like to add some water because that's what the reagents are dissolved into. So we tend to target between 1 and 1.25 pore volumes, which work out to binder ratios if you're dealing with 6% binder, in and around 3 to 4. Moisture contents, somewhere between 17 and 25, depending on how you're looking at it. but 1 to 1.25 pore volumes is what we tend to see people be able to go out in the field with. Okay, so the effects of water content. Why is water content important? This is why. This is UCS compressive strength. This is data generated in our lab. And as you can see, starting at about 0.8% of a pore volume and going out to 2% of a pore volume, you're seeing at 90 days, 1% per sulfate, 8% binder, going from 350 PSI all the way down to less than 100 PSI. So this is getting to be close to the final, actual weight. The curing, of course, keeps going, and it will continue to increase a little bit. But after 90 days, this is actually getting to be pretty close to the final. And you're seeing that you are dropping a very significant amount. Portland cement blast furnace slag seems to be a little bit more sensitive to it, but you can see Portland cement only, there's also a very significant drop. Now that little hitch between 0.8 and 1 pore volume, what's interesting is that it seems like that should be an outlier, but I've run this data on enough different soils, I see that pretty consistently. It seems like from 0.8% to 1%, there's no real effect with Portland cement. But as soon as you add the blast furnace slag, it does affect the strength going from 0.8% to 1%. So just a little side note, a little oddity that I do see, or I've seen at least 3 to 4 times, that little hitch right there in the Portland cement only is very consistent. Moisture content on hydraulic conductivity. Basically not, so it affects the compressive strength, but it may not affect the hydraulic conductivity all that much. Here's a couple data points going from 0.8%, 1.25%, and out to 2% with the Portland cement blast furnace slag. All of the data, again, 1% Portland cement, 8% binder, 28-day cure time. All of the data was, pretty much linear there, the blue dots. We did see some bounce with the Portland cement. I haven't seen enough data to say if that bounce is consistent or what may be going on there. But so there might be some variability with Portland cement only in hydraulic conductivity as a function of water. But right now, what we see is there's little effect with the Portland cement blast furnace slag. And overall, these are within an order of magnitude. So, and they're all below the common goal of 1 × 10⁻⁶. So in summary, ISS and ISCO are 2 mature technologies. ISS, I've seen people claiming that it's been around since 1940s and 50s, certainly commonly been used since the 1990s. ISCO has been around since the 1980s, people running around trying to use hydrogen peroxide, certainly came into its own in the 2000s and is currently one of the more common remedial technologies used to treat environmental sites. But what's interesting is that they can now be combined. We're finding that you can combine them and that there's this synergies between the two. There's literally benefits going both directions. ISS benefits from ISCO. And as we discussed here, ISCO, especially if you're going to soil mix, can benefit from solidifying after the fact so that you're not dealing with a complete mess of a site. The ISS, I didn't talk about the mechanism, but it's really kind of easy to explain. The analogy I use is a frying pan. If you don't want something to stick on a frying pan, you add oil. Well, here we want things to stick. And so the ISCO helps remove the oil that's already there. And the oil, of course, is the contamination or natural organic matter. By adding the ISCO, you treat that oil, you treat and reduce it, you treat the natural organic matter, which the binder's not going to stick to. You essentially clean the surface of the soils a little bit and you get a better cementatious process. So these technologies can be combined. The ISCO provides, the better, the ISS gives the geotechnical strength after soil mixing. ISS, there's the various benefits, reducing the long-term risk, lowering leachate concentrations, lowering the hydraulic conductivity, increasing the compressive strength, lowering the amount of soil bulking. And I really want to emphasize that water content is an important parameter that should be considered in all of these designs and bench scales. With that, I'll take any questions, if I still have time.
We have time. Thanks, Brent. Thank you very much. If you have any questions, please type away in the questions or the chat box and I'll get to them. Again, a copy of the presentations are available on the RemTech website. I'll send out the link later today along with a link to the video of today's presentations. Any questions for Brant? Brant, doesn't look like there's any questions.
Okay.
Well, we will move to our next presenter before our break. So up next is Paul Newman with ECT2. Paul, if you can bring up your presentation. Paul's going to be speaking to us on sustainable PFAS resin technology applied at multiple locations for military base aquifer remediation. Looks like your presentation's good to go.
That's a mouthful.
Yeah, it is. I got through it.
Thank you, Joe. Can you hear me okay?
I had a second coffee. Go ahead.
Okay. Okay, I'm just going to try and minimize my bar on the left here. Just bear with me for a second. I don't want to leave the webinar. Joe, how do you minimize the control panel up on the top right? I haven't used GoToMeeting before, or this particular program.
The fourth little icon over from there's X.
All right.
Yeah.
Good. Okay, we're good to go. Well, thank you very much, Joe and team. We're really happy to have the opportunity to go through this presentation again. I think personally this is a great idea to represent these presentations because on a forum where you've got several parallel tracks, it does of course give you the benefit and the opportunity to see other ones that you really wanted to see but you couldn't at the same time. So just want to thank the group again for this opportunity to present. So what I'm going to be talking about today is a military base in Southeast Australia, Royal Australian Air Force, Williamtown. And this is a site that has had multiple PFAS impacts, which I'll go through. And what ECT2 has done since 2017, we've deployed a number of different treatment systems to address both soil and groundwater and surface water at the base. So I'll go through the presentation and just a little of the background. ECT2 was formed in 2017, and the company is really formed to address emerging compounds. The company name is Emerging Compounds Treatment Technology. So it was really kind of developed at that time, really with an eye clearly on contaminants 1,4-dioxane and PFAS. So that's really kind of our wheelhouse, and I'll go ahead and dive in. Okay, so background and objectives I'll go through and then talk about really what is the central feature of the remediation approach out here. It was basically we've got multiple treatment sites at this Air Force base, and so we have individual treatment systems that feed into one central ion exchange resin regeneration system. So I'll talk about the concept of regenerable ion exchange and then talk a little bit more about the individual treatment systems themselves, looking at how we address groundwater, how we address surface water. I'll provide some information on system performance and then key takeaways. And I guess if there's anything that I would ask that this group kind of keep in mind today, it's really, this approach is all geared towards hitting the Australian cleanup goals and waste minimization, which really drives down life cycle costs on a large project like this. So just a little bit of background, Royal Australian Air Force, Williamtown, they use, like many other military bases, AFFF, resulting in impacts to both surface water and groundwater. And at one particular side of the base, which will show, you have surface water migrating through a number of channels off base. The Department of Defense in Australia was very proactive. They initiated an environmental investigation. They defined the nature and extent of PFAS impacts in surface water and groundwater. And it's one of those sites that you really don't want to have some people at your site. Erin Brockovich on the bottom left, she was actually at the site. And I was mentioning before, I think I've worked on 3 sites where she's actually showed up. So I don't know if it's me or not, but Anyway, AFFF impacts result from firefighting foams, and that's the primary source of contamination out here. So if we look at an overall plume dimension map, this is the RAF Williamtown, and you can see the outline of the base is in red, and you have the extent of PFAS impacts in groundwater primarily and surface water depicted on this figure. So there are really three areas that we'll talk about today. There's a former fire training area in the upper left portion of the base. Moore's Drain is located on the right side of the base, but you can see impacts extend well off base in a east-northeast direction. And then there's the southern area where AFFF and PFAS impacted groundwater has migrated off-site, and that's referred to as the southern area. So the objectives of the work out there is really a multi-stage approach to mitigate PFAS impacts. There's stormwater at Moore's Drain, that was the first one, and that's similar to what's being, how it's being deployed in the United States in terms of identifying risk to receptors. Those get the top priority in terms of funding and approvals for PFAS mitigation. So it's stormwater at Moore's Drain, groundwater at the other two sites, one at the fire training area, and the other site, stage 3, was groundwater flowing off base to the south. And as I mentioned before, featuring in concert with those three stages, we have a central ion exchange resin regeneration plant. The overall goals of the project were to reduce PFAS migration off-site in surface water and groundwater, removing PFAS from the source areas. It was also really to look at a cost-effective approach that would minimize PFAS waste generated. And the treated water criteria that we had as objectives were to meet the Australian health-based guidance values, which were PFAS and PFH excess are less than 70 parts per trillion or micrograms per liter, and for PFOA less than 0.56 micrograms per liter. So we refer to this in terms of the approach as kind of a hub and spoke system, wherein we have these individual treatment systems up here in the northeast, or northwest rather. You have a former fire training area, and we actually co-located the treatment system for the southern area at that particular location. You have the Moore's Drain location up here, and southern area extraction area to mitigate offsite migration to the south. And then we have this central regeneration plant. So refer to as hub and spoke because, you know, the hub would be kind of the central regeneration plant, and the treatment systems kind of feed into that central regeneration plant. And the concept behind the hub and spoke system and the regeneration system is that ECT2 has ion exchange media that can be regenerated rather than disposed of when it gets spent. So the idea is when the system is operating, you have influent water coming into your vessels, your pressure vessels filled with this regenerable ion exchange media, and clean treated water comes out. So once that vessel gets saturated, where you get breakthrough, and you typically have kind of a lead lag arrangement for these vessels. So once sampling indicates that your lead vessel, you're starting to get breakthrough, you actually take that offline and put in the lead vessel. So there's no loss in operational efficiency, there's no downtime. So what happens is, so once you have that vessel generation kind of on skis is spent, you take that to the regen facility, as you can see. So a forklift can lift these up and they can go on a flat system. So at the regeneration plant, what actually happens is you have a regenerant solution that is passed kind of in a counterflow direction through that ion exchange vessel. And what that does is basically strips off the PFAS constituents from the ion exchange media. That solution then gets distilled down, creates still bottoms, and then the waste is actually loaded onto another media. And then so that system is basically cleaned and the vessel flushed and then taken back into service. So what that does is basically you have high removal efficiency with the ion exchange, and it's particularly good for short chain compounds. And as you look down the road as to what PFAS constituents are going to be regulated in the future, you know, increasingly PFAS constituents are going to, the short chains are going to be of concern. Type of situation, you know, you wouldn't install this single location. It would be this type at a probably more applicable where you have multiple individual locations, and so military bases are a good application of that. Or if you have a number of different sites within, say, one region, you can still have a central regeneration plant. But this is geared more towards higher concentration of PFAS, where you have, say, greater than 10 million or micrograms per liter. And what this does is it produces a waste that is very, very highly concentrated. So as this group is probably aware, there are many research efforts underway to look at disposal technologies rather than putting it in a landfill. Plasma, I think several other individual companies are exploring these. So, it really provides a really high concentrated waste that these disposal or destruction technologies can be deployed on. So that's kind of the concept of how the regenerable process works. So the regeneration plant that we have at this particular location, this is what it looks like. You've basically got a Connex box, and at all of these locations that I'll go through today, we basically constructed these Connex boxes in Portland, Maine, and put them on a Sikorsky aircraft and sent them across the world to Australia. So that's kind of what the regeneration plant looks like. And this is the inside of the Connex box where there's the distiller. So this central regeneration plant services all three treatment systems on the base. And so the regeneration solution reused, it's a closed loop system, so there's nothing lost. And the key thing here is waste minimization. The process of the ion exchange resin in concert with the central regeneration plant really minimizes waste. So the process generates about 1 gallon of PFAS waste per million gallons of water. So, as an example of that, we have another site that we've been operating in New Hampshire, where we've been operating since 2018. We've treated over 40 million gallons, and we have generated only 40 gallons of PFAS waste, and we've been non-detected effluent all the while. So again, it really concentrates the waste, and it really minimizes what's going to have to be sent off-site or disposed of down the road. And that has significant life cycle cost benefits, which I'll touch on a little bit later. So that's kind of how the regeneration system works. So now I'll kind of quickly go through the individual treatment sites themselves. So the Moores Drain up in the northeast portion of the base, this is one where there were surface water impacts and they were migrating off-site. So we started operation there in 2017, and originally it was more of a demonstration project. They wanted us to put in a system at 50 gallons per minute flow capacity. And based on the results that they saw, they said, let's go ahead and upgrade the system to 130 gallons per minute in April 2019. And what we were actually able to do is, if you look at the Connex box in the central portion of this figure, that was the 50 GPM flow rate system all in a box. When they wanted that upsize to 130 GPM, we were basically able to add the additional valving and vessels on the outside to provide that increased capacity. Not probably, it's certainly something you can do in Australia. Have challenges doing it in northern Alberta in the winter, but that's the concept. These are very scalable systems that we implemented out here that deploy the same technology basically in each individual treatment system. So we got the system up and running within 4 months of contract award. And one of the things that we always look at when we're designing a system, pre-treatment requirements for particularly for ion exchange technology, it's a big deal because you have to kind of protect the resin. That's always the saying I think we have, where you don't want the resin fouling you. And so, iron is a big deal that you have to be aware of. So we always go through a comprehensive exercise of defining influent water quality and what sort of pre-treatment scheme we need to have up front, whether it's sand filters, backwash in concert with backwashable granular activated carbon. But the media that really does the heavy lifting as far as the PFAS is concerned is the ion exchange resin. Inside some of the we've actually had, I think, eels at this particular site in the influent pump. So, this is some of the performance data starting back in, this is 2017 going through 2020. Not a particularly interesting graph in that it's pretty consistent. The influent quality, it varies between 2 to 10 micrograms per liter at Moores Drain. And we've been consistently below the health-based guidance. Next, former values since inception. The next site we'll talk about is a fire training area in the west portion of the site of fire training exercises. So groundwater was impacted, very shallow groundwater table. And these systems, again, look very similar in terms of one site to the other, where we deploy these initial Connex boxes with vessels and appurtenances just under a shelter. So we started in 2018, the influent concentration, the basis was between 10 and 500 micrograms per liter. This system operates at about 200 gallons per minute, and we're able to reuse water on site and via a sprinkler system, basically a spray field. What's kind of interesting about this site is when we got on at the site, so they had a surface water treatment system adjacent to the fire training area as a result of historical impacts as well. So if you think of what technologies could be deployed to treat PFAS and maybe what the footprint might look like, these photographs on the right are actually the exact same scale. And these are a lot of granular activated carbon vessels. And this is just literally like a couple hundred feet down the road. This is what our system looks like for groundwater. And that basically treating the same sort of flow rate, roughly the same, certainly the same order of magnitude of PFAS influent. And if you look at the waste generated, this is something to really key in. The waste generated at this particular fire training area with the GAC system is about 914 tons, and we to date have generated only 7 tons of waste. So as you can say, a very substantial decrease in the amount of material that would eventually be disposed of or destroyed. And then, if you're looking at building a groundwater treatment plant as well, if you're putting vessels inside a treatment plant as an example, I mean, the smaller footprint of ion exchange definitely will result in a smaller building footprint. So, the vessels are smaller, 14 feet typically, GAC maybe up to 27 feet. So there are savings associated with the building sizes, which has, sustainability goal credits related to that. So similar sort of thing, the influent concentration at the fire training area, this was between 15 and 55 micrograms per liter. We've consistently, you can see, basically been flatlining with our effluent below the health-based guidance values. We're basically non-detect all the way across. So very consistent data. In the southern area, this is the area where we also put in a treatment system adjacent to the fire training area. And the idea, similar sort of design basis. And what we did is put it in there because we able to share capabilities, same O&M operators, shared utilities, we minimize the footprint, capital and operating costs, and same sort of thing, treated water is returned via a sprinkler system on site. And pretty similar, consistent data since 2019, the influence between 10 and 20 micrograms per liter, but we've been able to maintain the effluent below Australian health-based guidance values consistently. So if you look at what the implication of say, a regenerable solution, this one is not at Williamtown, but I thought this would be instructive to understand what the implications are of implementing, say, a regenerable solution. You're going to have a capital cost associated with the regeneration plant. But on a site like this, where you have, say, total influent in the 50 ppb or microgram per liter concentration range, and you're looking towards the objective, say, in the United States of 70 nanograms per liter combined or individual, if you look at, say, a 20-year life cycle cost value, even though we've depicted here what orange depicts granular activated carbon, RO here in blue, and then single-use ion exchange, and then regenerable ion exchange in yellow. So what you can see is that as the quantity and as the duration of treatment extends further out, the life cycle cost savings are pretty significant of, say, a regenerable ion exchange solution versus, say, certainly granular activated carbon solution. That's really because, I mean, in a nutshell, you're not taking the granular activated carbon and shipping it off-site. You're not taking the ion exchange resin and shipping it off-site. You're reusing it each time. So it's a very sustainable solution. So the key takeaways, regenerable ion exchange is really, really good at treating PFAS constituents. It has a high capacity for PFAS compounds. It works really well. And you can have extended run times between regenerations. And as I mentioned before, pre-treatment is really, really important when you look at the individual water quality characteristics and what you need to do upfront with the resin to make sure that you can have effective uptime of your systems. And in this particular case, the treater water management system, we were able to reuse water on site. And so that scored well from an Australian sustainability goals perspective. And really what we did is this demonstrated the capability to consistently meet performance standards with really low waste production, which drives really, really low life cycle costs. And as I mentioned before, what we're seeing is a typical 1,000,000 to 1 sort of waste concentration factor. 40 million gallons treated at Pease Air Force Base, as an example. With no detections above criteria, we have generated just 40 gallons of waste in probably over 3 years of operation. And it's kind of interesting when you take people to see the site and they say, well, where did all the PFAS waste go? And you point to a small drum over in the corner, and like that's all there is. So very sustainable approach in terms of remediation, and with continuing concerns as to, well, if you're going to put this stuff in a landfill, what are the long-term consequences of destruction or semi-destruction of the PFAS constituents and dispersion? It's a very sustainable approach towards PFAS remediation. So with that, just wanted to show, this was typical treatment systems where they're shown underneath a canopy, and this was actually a Sikorsky aircraft where we loaded about 3 or 4 of these containers and flew them around the world. So we're very excited about the work that we're doing here. In Australia was really ahead of the curve in terms of implementing remediation technologies for PFAS, and so we're kind of leveraging that to deploy it elsewhere right now. So in Europe and the US, so very excited about the path that we're on, and I'd be happy to answer any questions.
Thanks, Paul. Great presentation. Great to see a presentation on a project somewhere outside of North America on a topic like this.
Sure. Thanks, Joe.
Yeah. Any questions? Feel free to type them in the chat and we'll get to them, or the question box. Anybody have any questions for Paul? Well, his contact info is on the screen. So thanks again, Paul. We'll take a break now. We had scheduled a break till.
My pleasure.
Yeah, we're early, so we'll meet back at let's say 10:40. So instead of 10:45, we'll meet back at 10:40. Give everyone a little bit extra break. So we'll see everyone back in 20 minutes.
Thanks again, Joe.
Thank you. For our next presenters, Dee, Brick, and Terry, just to let you know, we'll be starting at 10:40 in a few minutes early because we ended early on the first session. Everybody else who's waiting, we'll get started at 10:40. Stay tuned. Welcome back, everyone, to our webinar series, and our next 4 presentations for today, our last 4. Thank you for your patience so far. Glad you could make it. Once again, the webinar is sponsored by our good friends over at Trace Associates, so thank you to Trace. Our next presenter is Deeb Burkholz from Deeb Chem Forensics. Deeb is going to be talking to us today about gasoline forensics, source identification for low-level groundwater contamination. I'll turn it over to Deeb. Deeb, go ahead.
Joe, can you see the screen?
We sure can. You sound good. It looks great.
Okay. Well, anyway, I want to thank Joe and Isa for allowing me to present. And I also want to thank my co-authors here, Dr. Relich from Parasol Labs, Jessica Arthurs, and Alex Wood from LRL Associates Limited. One of the challenges that we're seeing here is, Joe, how do I get rid of this thing on the top here? You got a little box and an X, audio view and all that. Joe?
You can drag it and move it aside.
Yeah,
Just don't hit the X.
hit the X.
Don't hit the X. Just drag
Oh.
it and move it aside or out of the view.
All right. One of the challenges that we're seeing is that environmental regulations are getting more and more stringent. And one of the things that we're seeing it happens is in Ontario is stipulating maximum levels of petroleum hydrocarbons on sites. And in other words, tables are provided by MOE to consultants, and they basically stipulate various generic site conditions which may be applied to a contaminated site. And these tables depend on the drift thickness, proximity to surface water body, soil texture, water usage, and also potable, whether you have potable or non-potable water in the groundwater. Now, depending upon which table is applicable, you could have PHC F1 concentrations that are significant. In other words, are trigger values with levels as low as 420 to 750 micrograms per liter, and PHC F2 concentrations of 150 micrograms per liter. Now, exceedance of either of these values generally requires further delineation, either remediation or risk assessment. These low levels really provide strong analytical challenges to labs that are engaged in forensics. In other words, trying to determine source delineation. Who's responsible for this material? Who's going to pay for the cleanup? Now, one of the things that we look at when we're doing gasoline forensics, and this is a wish list, okay, I'll repeat, a wish list, is we deal with process forensics. In other words, how is the gasoline made? If you have gasoline from two different sources and they're made differently, then they're clearly different. So we look at things like reformate, alkylate, fluid catalytic cracking, isomerization, butane blending. We can have simple refineries or we can have complex refineries. And the point is that you're going to see differences in the distribution of these blending stocks. Usually the first step that's ever involved when you do forensics is you get BTEX F1 and F4, and I've got to be honest with you, I do a lot of this type of work, and this is a lot of information that I'm provided. And it's not designed for doing forensic analysis. These methods stipulated by CCME are designed to determine whether you have contamination and whether that contamination exceeds some guideline. They were never ever designed to do forensics. In other words, we've got samples from various wells and we want to know if the gasoline's the same or different. The method this is the kind of data that we really want to gather. Again, it's a wish list. We use piano analysis, and we look at things like paraffins, isoparaffins, aromatics, naphthalene, and olefins. Piano tells us a lot about the process. We talked about process forensics. Organic lead is very, very important. In other words, are we dealing with leaded gasoline? And we can look at different lead alkyl types. Presence of oxygenated additives, MTBE, TAME, ethanol, methanol. I've done a ton of these things, and usually in groundwater, I never see them, but that doesn't mean you won't find them. You can do bulk carbon and hydrogen analysis, isotope analysis, and then some additives, alkyl lead, MTBE, have time restrictions, so you can make some kind of estimation on when this spill material was released. So some of the things that we look at in process forensics, again, this is a wish list, okay? We look at things like butane blending, isomerate blending, alkylate blending, naphtha reforming, fluidized cracking, and then octane enhancers. Again, these are things that are critical to how the gasoline is made. It may be, if you have gasoline from different sites that are made differently, then clearly different. And these are the kinds of chemical ratios that we can look at: 2,2,4-trimethylpentane over methylcyclohexane, 2,2,4-trimethylpentane over toluene. You can look at butane blending, isomerate blending, reformate blending, et cetera, et cetera. This is the kind of information that we aspire to, but we might not be able to get it, again, if we're dealing with low concentration levels of gasoline. Here's 9 different gasolines where we basically accumulated this kind of data, and you can see where we're coming from. We got isooctane over MCH, octane index, butane ratio, isopentane index, toluene over NC8, blah, blah, blah. All of these things that are very, very specific information that designed to tell us how the gasoline was made. And we can see some similarities for gasoline A, B, and C. We can see similarities for D and E, and then we can see a lot of dissimilarity for F, G, H, and I. Why we would have these are from 3 different stations. These are because the reality is today a lot of vendors get their gasoline from jobbers. In other words, bulk fuel facilities that provide the same gasoline, even though they may be different vendors. So we have 3 of them here, we have 2 of them here, and all these other ones are all different. Now, going back to our problem here, we have low levels of hydrocarbons in the groundwater, and it's above a trigger value. So some action has to be taken, reclamation or risk assessment. Here's your source. This would be the release. It might be a large tank. It might be millions of gallons if you're dealing with a bulk facility. And as it moves away with groundwater flow, you get a thinner and thinner lens. Here you're going to get a lot of information. You're not going to get a lot of biodegradation. You may get some evaporation. As that lens gets thinner and thinner and thinner, you're basically stuck with chemicals at the tail end of the gasoline. In other words, those that are the least water soluble, those that are least biodegradable, and those are the least that will evaporate. This is the area that we're basically dealing with when we deal with low levels. In other words, the site has very low levels of hydrocarbon, as opposed to a monitoring well where we might have millimeters, centimeters, or meters of LNAPL floating on top of the groundwater. Now, there's several ways to do these gasoline analysis. In other words, source spill. In our case, we've got sample from a number of wells. We want to know if they're the same or they're different. If LNAPL is present, this is always the golden standard. Then we have a variety of methods. We can use a PONA column with a mass spectrometer on the end. We can use purge and trap, but here getting the concentration is right. We'll talk about that a little bit. You can analyze by GCM headspace. If no LNAPL is present, then GCMS purge and trap is one of the recommended methods. Or we can extract the groundwater and employ GCMS using a PONA column. But because the PHC values are low, what we did is we proposed concentrating the groundwater samples during collection. In other words, we collected multiple composite Baylor samples up 1620 and extract the concentrated hydrocarbons using an ETFE net, ethylene tetrafluoroethylene. ETFE netting has been reported in the literature for use in collecting gasoline, but we have no data. It has been used extensively, though, by the Oil Spill International Network. And we propose using ETF netting in combination with passive headspace because better precision, as you'll see, relative to solvent extraction and concentration was observed. So purge and trap is one of the recommended methods. There's an enormous amount of literature on it. There's books been written on it. However, based on the publications, and Scott Stout from Newfields has published extensively and written chapters and books on it, concentration is the real issue. So levels below 500 micrograms per liter may not provide sufficient chemicals. And if you have BTEX values of less than 100, it might not be very valuable. All of the literature that's been written, and Scott has published a lot of it, they're talking about values that are way above that, like 6.3 to 160 milligrams per liter. We're way lower than that. So we really wonder if purge and trap would be useful, and you know, how many chemicals are you going to actually detect? The method purge and trap GCMS for gasoline basically reported 23, evaluated the method by using NIST standards, and they looked for 23 analytes out of 109. But they did get some very useful information which we applied, and that was the relative percent difference between samples and also the RSD, relative standard deviations. So the RPDs not to exceed 25%, RPD values of less than 15% are desirable. Now, we didn't use purge and trap, and a lot of the labs in Alberta have gone away from this. simply because they were problematic. I mean, if you're in Ontario, it might be different because the groundwater tends to be a lot cleaner. Alberta is oil and gas country, and that's not the case. So we end up having problems a lot with overloading the system and having to decontaminate it and getting the concentrations right. And it causes not only frustration for the lab, it causes more frustration for the client because you continually call them and tell them that the results are going to be late. So many of the labs have gone away from this technology completely. A lot of them have gone to GCMS Headspace, which gives comparable data. Now, the netting that we prepared to use has been used by the Oil Spill International Network, of which I'm a member. It's been around since basically 2000. It's been recommended by Stout in his massive chapter on gasoline, but no data was really provided. We know recently from some very recent papers that similar type of material, hydrophobic pads, have been used, and those have been basically processed using passive headspace. Passive headspace is used for fire debris analysis. We've done a lot of these when I was with ALS, and then there have been a countless amount of information on it. And what we were really interested in was using these technologies, ETFE netting, extracting large volumes, and then passive headspace, and then looking at alkylated naphthalines. Sandercock, he's now retired with the RCMP, published a lot of papers on this, and he also wrote a chapter in the book. So because we had two well-established methods under ISO Guide 17025, all we had to do was a validation study. So what we did is we collected samples, or Milan did, from the Hamilton area, Esso, Costco, and Pioneer. And here's some data very, very quickly looking at process forensics. And you can basically see that these are all very, very different. I mean, they give very different values. And we're getting information on the amount of reformate conditions, the amount of alkylate, amount of isomerate, straight run gasoline, reforming conditions, et cetera, et cetera. So what we did is we took a mill of the gasoline samples, we added it to 500 mils of water, we mixed the gasoline and water, we extracted with ETFE netting. The netting was stored in a jar for several days because that was reality based on what we did in the field. After the addition of surrogates, we placed it in a 1-quart can. We added a carbon strip. We heated it to 80 degrees overnight. The carbon strip was retrieved, and we analyzed by GCMS scanning using a PONA column. This is basically the same kind of process from here on that you use for arson investigations, of which we did a lot. So here's a picture of what we have here. We extract the sample, it goes in a jar, then we add it to a 1-quart paint can, we add surrogates, and then what we do is we take activated carbon, put it on a bobby pin, bend it, attach it to the bottom of the lid, and then hold it in place with a rare earth magnet, a strong rare earth magnet, seal it and put it in an oven. And so what ends up happening, get this stupid thing out of here, is that here's your can with the carbon strip on the end. It's heated at 80 degrees overnight. You retrieve the carbon strip, you add it to a vial containing carbon disulfide, an internal standard, and you basically analyze it by GCMS. Now we see some very interesting things on what's happening. Here, this is the gasoline sample, Esso gasoline, that we run split with the PONA column. Usually the split's about 200 to 1. Here's the passive headspace. In other words, we add it to a chem wipe, and then it's collected on a carbon strip and analyzed. And what you see is a shift towards the right in order to the heavier end, the so-called tail end of gasoline. Then when you combine the technology of a net and the passive headspace, you move even farther to the right, and you end up seeing much heavier material. The question is, what valuable information can we get? Is any of this going to be useful to give us process forensics? Are we going to end up getting that kind of information to compare samples? Well, yes. Here's your N-alkanes. You don't really see anything till CN10, but this is gasoline. It's supposed to be done at CN12. We're seeing responses up to 14. We see strong response for cycloalkanes, strong aromatic. These are all alkylated benzenes, your indane profile, and your alkylated naphthalines. The alkylated indans are quite interesting. They may be derived from various different processes, how much straight run gasoline reformate how much, reforming conditions if they use hydrocracking, cat cracking, etc., etc. So you can clearly see between the three gasolines, they're very, very different. Now, does the OxyNet process, you said that's what you used, Oil Spill International Network, use passive headspace? No. They rinse with dichloromethane. And why didn't we follow this? Why did you adopt for passive headspace? Why did you deviate from what these guys recommended? And they've used this process for over 20 years. Well, here's the reason. So here's where the nets were basically washed with DCM and concentrated. Here's where the nets were basically subjected to passive headspace. So without spending a lot of time on this, you got Esso, you got Costco, you got Pioneer, and you also have the mean values here. One of the things that sticks out right away is that your precision increases immensely when you basically apply passive headspace, as opposed to what? Rinsing the net with solvent and concentrating. And that's not, from a chemist's point of view, that's not surprising at all. And then here's the reason that we processed ETF passive headspace. Again, we're seeing these are alkylated benzenes. We get much better precision when we basically combine the net with the passive headspace. These are the chromatograms for alkylated indents. I'm not going to spend a lot of time on it, except to illustrate what we observed, and that is, if you look at the peak heights, this is gasoline split. This is a gasoline put on a Kim White passive headspace. This is gasoline extracted with a net and put in a can. We see an immense increase in sensitivity. Signal to noise has increased phenomenally, which is, any chemist would love to see that happen. When we look at the alkylated benzenes, we basically see the same thing. We get a much stronger response here. This is well over a million here compared to what we started with for the alkylated benzenes. Gasoline split, passive headspace, ETFE, passive headspace. The other thing is comparing what we're doing here, ETFE netting followed by passive headspace. Is this some kind of a weird new method? Well, it is a new method, but it really isn't, in the fact that somebody else in 2020 published this using hydrophobic pads. And basically what they're looking at is they're looking at fires, and you got an enormous amount of firefighting equipment and a lot of water that's generated, and they want to know, was this fire deliberately started? So they're starting to look at the wash water from fire mitigation processes to see if there's evidence of the fire being started. Here's your alkylated benzenes. Again, you see a much higher response, a mass 119. When we compare the split, 102856 to what we're seeing here, well over a million when we use the net and passive headspace. This thing is really annoying. And when we're looking at naphthalene, very, very important. It's one of the process chemicals that we're interested in. We actually see that the concentrations, 28,656 increased to over 424,000 when we use the passive headspace extraction with ETFE netting and passive headspace. Alkylated naphthalenes, we see the same thing. These are your methyl naphthalenes. We're seeing a much stronger response. When we look at 156, these are your dimethyl naphthalenes, very strong response, much stronger response. Can hardly even see, the peak shape is horrible here. Absolutely horrible when we do it split, because these concentrations, these chemicals are present, but they're not very high concentrations. When we go to the ETFE netting passive headspace, they're actually concentrated quite a bit. And these are compounds that the Oil Spill International Network uses a lot for forensic analysis. In other words, we glean ratios from them to determine similarities or differences between spill and sources. Then the bonus that we got actually was trimethyl naphthalenes. You can hardly see them in passive headspace now. So here we're adding the gasoline to a Kim White and heating it. You can see a much stronger response, a better response when we're looking at the ETFE netting and the passive headspace. In other words, the ETFE netting is actually concentrating a lot of these materials. So when we look at various ratios and we look at the RSDs, relative standard deviations. We did a lot of replicates of these, the ESSO, the Costco, the Pioneer. If you look at the different ratios in the RSDs, we're pretty, this is neat. In other words, this would be split. This is the gasoline added to a Kim wipe and basically using passive headspace. And then this is the ETFE netting with passive headspace. We're quite happy with the RSDs that we're seeing. Going back to the criticism that we may get in a litigation case, this is a litigation case. The criticism that we may get is, well, how well does it perform against purge and trap? Well, you didn't use that. Well, based on the evaluation of that method, we're fine. We're well below 25%. Most of them are below 15%, and in fact, a lot of them meet AussieNet standards where we're 5%. So we're quite happy with what we've seen here. And here's the total results for all of the samples. This is the ETFE netting followed by passive headspace. You can say these are your alkylated benzenes that we're seeing up in naphthalene over dodecane. These are your alkylated naphthalenes that you're seeing. And you can see the RSDs certainly meet the criteria, below 25%. A lot of them are below 15%, depending upon what we're looking at. Now, you're saying, well, this isn't very good when you compare it to Costco, but let's go back, folks. What did we talk about process forensics? Gasoline is not gasoline, is not gasoline. It may be made differently. Your reforming conditions, how much reformate that you have and how it's made is going to dictate what your precision is going to be. You know, we get much better precision over here with the Pioneer than we do, let's say, over here with the ESSO. And that has nothing to do with the method. That has everything to do with how the gasoline is made. We see for some of the other chemicals here that we get very, very good RSDs. I've highlighted some of them that would be very, very useful to use from a process forensics point of view to determine whether this gasoline obtained from this well at low levels is the same or different than gasoline gleaned from another well. Now, here's some usable source apportionment ratios that we basically suggested, and there are others that we could use as well. You don't see a lot of indans on here, but we certainly could add more to that. So we've got from a weight of evidence point of view, we've got a pretty good choice of ratios that we can use, which is consistent with the Oil Spill International Network way of doing things. In other words, looking at ratios and looking at ratios that are stable. This is kind of a silly slide, the quality control. It just basically goes to illustrate one very, very important point, and that is you're basically applying a net to water. Some water, not a lot, is going to be entrained. It could deactivate the carbon strip, and you could end up with erratic data all over the place. Well, we didn't see that. We didn't see that at all. And neither did they with those hydrophobic pads. So this just goes to illustrate that we're not too concerned about that. So we can conclude here the extraction of water samples containing low levels of gasoline can be performed using this AussieNet ETFE, ethylene tetrafluoroethylene netting. The gasoline is extracted and concentrated using passive headspace. We do use a PONA column to give maximum resolution. The RSDs and the relative percent differences are consistent with the purge and trap method, which is really the only yardstick that we have to go against. The netting actually concentrates some analytes from water, namely alkylated benzenes, alkylated naphthalenes, alkylated indanes, and this results in a greater signal to noise response and increased precision. So there's my coordinates if you have any questions. And then going back to the plume delineation model that we had there, if you're going to see a small lens of hydrocarbons floating on top of the water that have migrated substantially from a source, you're going to see a lot of these heavier compounds. You should be seeing a lot of these heavier compounds that are, more resistant to evaporation, more resistant to water washing, more resistant to biodegradation, and the netting seems to key in on those things. Anyway, with that, I'll thank you, and I'll be glad to entertain any questions. There's my coordinates if you want to deal with me, either on the phone or email me or whatever. Thank you.
Thanks, Deeb. That was great. Anyone have any questions for Deeb while we have him here and take advantage of his knowledge? Okay, so, Deeb, no questions at this point. So again, reach out to Deeb. His email is and contact her on his presentation, and I'll be sharing the presentations later. So thanks again, sir, and we'll move on to our next presentation. Our next presenter is Terry Obel with Bureau Veritas Laboratories. Terry is going to be presenting today on total organofluorine analysis by combustion ion chromatography, a new tool for monitoring PFAS impacts. So we'll get Terry get his presentation up and we'll get going.
Great. Joe, which screen are you seeing? So I got multiple screens.
Your desktop. Your desktop.
Okay. Is there a way I can shift to another screen?
You had, I saw it on the bottom come up.
There it is. Sorry.
That's okay.
Well, you know what? I'm just going to make a quick adjustment here.
Yep. Yep.
Just bear with me.
Yep.
There we go. So this should do better. Now you should see a title screen.
Perfect. Thank you.
Great. Thank you. Thanks everybody for your patience with me there. Are we on time to start, Joe? Or
Yeah.
yeah.
Go ahead. We're running early today, which is great. We'll get done early today for everyone, so it's good.
Well, I'll fix that. So
Okay. I knew you would.
yeah. Listen, thank you, Joe. Thanks for the opportunity to present on total organic fluorine analysis by combustion ion chromatography, and I thank everybody in attendance. It looks like there's a good number logged on, so I appreciate you taking your time out of the busy day. A significant effort continues to be focused on delineating the extent of contamination by individual PFAS compounds. An additional difficulty that may influence PFAS remediation efforts is the potential for in situ transformation of the larger, higher molecular weight PFAS precursor compounds to the smaller, persistent PFAS of concern. And this introduces potential future risk and liability for the site owner. So most of these precursor compounds are not included in the suite of PFAS routinely measured by commercial laboratories. The analytical challenge is accounting for these precursors in addition to the suite of target PFAS currently being measured. In other words, what is the total PFAS impact on a sample? So today, I'll be presenting on the current offering of tests or tools available for determining PFAS in a variety of matrices and for a variety of needs, highlighting Bureau Veritas's ability to gauge the magnitude of total PFAS, including non-target PFAS, in environmental matrices using total organic fluorine analysis by combustion ion chromatography. So the scope and complexity of the problem this class of compounds presents for analysts and for environmental stakeholders has grown over the years. Where it began many years ago was with two compounds that gained some notoriety in the press, PFOA and PFOS, or perfluorooctanoic acid, and perfluorooctane sulfonic acid. But very quickly, the need to measure other PFAS grew with the recognition that the environmental issue was far more complex than just PFOS and PFOA. So laboratories began developing methods to measure other perfluoroalkyl compounds, examples being perfluorobutanoic acid and perfluorononanoic acid, among 24 or so others. The complexity of the problem continued to evolve with the question of, where are these compounds coming from besides direct sources? And this led to the need to measure precursor compounds. These are polyfluoroalkyl compounds, which can over time transform to the more recalcitrant perfluorinated compounds. And then as the public and the manufacturers of these compounds recognized their probable environmental and human health risks, they began eliminating their use in manufacture. And in doing so, they developed replacement compounds. And these are the compounds with cool names like Gen X and Adana that were arguably, I underscore the term arguably, less toxic and posed a decreased risk. Evidence is actually showing quite the opposite. All in all, the class of compounds, PFAS, is represented by more than 5,000 compounds, many of which can transform over time to the recalcitrant end products, which are increasingly being regulated in a growing number of jurisdictions. Now, the evolution of the PFAS toolkit paralleled the growth in environmental interest in PFAS. With that said, it's important to understand the different techniques available to characterize and delineate PFAS contamination. The most common analytical technique used to measure PFAS is liquid chromatography coupled with tandem mass spectrometry, or LCMSMS is the acronym you'll hear. This technique, it's a targeted analysis. So what that means, it's measuring individual known or target compounds. And the current suites of target PFAS analyzed by commercial laboratories typically number between 20 and 40 individual compounds. With the recognition that the scope and magnitude of the PFAS problem extended far beyond the routinely measured PFAS compounds, that 20 to 40 compounds, an approach was developed that provided an indication of PFAS impact on a site beyond the limited list of target compounds. Hence, the total oxidizable precursors, or TOPS assay, was developed. In this case, duplicate samples are analyzed as received and after oxidation using LCMSMS. So changes in PFAS concentrations after oxidation, particularly with the shorter chain carboxylate compounds, these are the carboxylic acids, it indicates the presence of other PFAS beyond the limited target compound list. So in other words, they've converted to the recalcitrant end products, and these may present potential future liability. Basically what it's doing is it's modeling how these compounds may behave in situ. So in other words, on site, if you clean up just for the target compounds and don't consider larger compounds that aren't measured by LCMSMS that may over time transform to the end product, you run the risk of future liability. So to address some of the limitations inherent in the TOPS assay, and there are limitations, techniques have been developed to measure total PFAS in samples using the organic fluorine content in the sample as a proxy for PFAS, given that the majority of organic fluorine stems from PFAS. So different techniques have been developed to do so, including neutron activation analysis, particle-induced gamma ray emission spectrophotometry, commonly referred to as PIGGY, and combustion ion chromatography. Neutron activation analysis and PIGGY present some significant barriers to entry. Neutron activation analysis requires access to a nuclear reactor to activate the samples, while PIGGY, it's got a significant capital component to it and complex instrumentation. Combustion ion chromatography, however, it affords a more cost-effective, read cheaper, and far less complex approach to measuring total organic fluorine, and based on the mass contribution of fluorine, a measure of total PFAS. So when we look at the applications, where are these different tools applied? PFAS by LC-MS-MS. So the first one, where you're just looking at a list of compounds, it's most often used for demonstrating regulatory compliance. So in other words, as I said, more and more jurisdictions are regulating these compounds. They're going beyond health advisory or screening limits and actually regulating. In Canada in particular, British Columbia was the first province to regulate 3 compounds, PFOA, PFOS, and PFBS, or perfluorobutane sulfonic acid. Most recently in July, in Atlantic Canada, the Rebecca environmental quality standards now include PFAS compounds at different concentrations, and CCME has now published environmental guidance for PFOS in waters and soils. But what's important to note is the levels that are being regulated. You are down at the low parts per trillion, and in order to do that, it's recognized that the current best practice is using liquid chromatography with tandem mass spectrometry, actually isotope dilution, LC-MS-MS. I point out here, where this is going, and it's evolving very quickly, is that North Carolina now is looking to regulate some of the replacement compounds, Gen X in particular. It makes total sense because Gen X was manufactured by Chemours in their Fayetteville, North Carolina plant, which is the center of productions like the Netflix production, The Devil We Know. When it comes to the TOPS assay, as I said, you're running a sample twice, once as is and once after oxidation, to accelerate and model how it's going to behave in situ. So what's important to note in terms of how this test is, or this assay is applied, is the first analysis, it gives you a baseline concentration of a target list, as you can see, a list of target PFAS. And then the duplicate is submitted for oxidation at elevated temperatures using persulfate and alkaline conditions, and then after 6 hours you quench it. And like I say, that is supposed to model how the sample is going to behave in situ. And what I want to highlight here is in the pre-oxidation, the as is or as received concentration, you have 2 precursor compounds that are included in this list, 6,2-FTS or 6,2-fluorotellumer sulfonic acid and 8,2-fluorotellumer sulfonic acid. Notice that in the first duplicate, you have concentrations about 200 and 400 parts per billion of these precursor compounds. Then you analyze the duplicate sample after oxidation. And what I want to highlight here is those precursor compounds, 6,2-FTS and 8,2-FTS, have gone down to non-detectable concentrations, whereas the lower molecular weight carboxylates or carboxylic acids have skyrocketed. And what that tells you is that you have PFAS in your sample over and above the target list presented on the left that are not being measured, that are not being captured in the first analysis. So I'm going to stop at this point just to speak to the concept of PFAS dark matter. So as we've discussed, targeted PFAS analysis using LC-MS-MS typically reports 20 to 40 individual compounds. Now there are exceptions. Test America, or not Test America, Eurofins is suggesting that they do 75 compounds. and that's fine. I mean, we're having trouble getting our head around the 6 or 9 that Health Canada has published. But most commercial laboratories typically report 20 to 40 compounds, and it will be 40 moving into 2022 with the publication of US EPA method 1633, which has a parameter list of 40 compounds. Yet we know that there are thousands of unknown PFAS compounds present in the environment, and these are sometimes referred to as dark matter. And so it's been demonstrated by that many of these unknown compounds can transform in situ to more persistent end products that are increasingly being regulated due to probable health risks and likely health risks. So with that said, how do you accurately assess the risk posed by a site and what the appropriate remedial action should be when you've got this kind of unknown? In other words, you know what the concentrations are of the target compounds, but you have no idea of other PFAS that may be present that may over time transform, or on its own may present a health risk. So the TOPS assay provides an indication of PFAS impact beyond the target compounds. However, it does not, sorry, spoiler alert, it is not fully quantitative. You know, sometimes leaving gaps when you try to do a mass balance between the results. There's sometimes high sample variability depending on the heterogeneity of the sample, or if you've done something like ISCO, in situ chemical oxidation, sometimes that throws off the results, and you're not really you're not sure that necessarily captures all of the dark matter. So what's the answer? Test for total organic fluorine. If you can partition the organic fluorine from the inorganic fluorine, then, you know, with the notion that the majority of organic fluorine in environmental samples is going to come from PFAS. Now, there are some fluorinated agrochemicals, there are some fluorinated pharmaceuticals, but the likelihood of them materially impacting the total organic fluorine concentration is low. So the answer is total organic fluorine. Just to give you an idea of what that means, is you're taking your sample, and if it's a soil, you're extracting it. If it's a water, then you are absorbing the organic fluorine onto a media. That media is then put into a furnace, a high temperature oven, a combustion, and you're combusting it. And those who look at treatability of PFAS, there's certainly all sorts of opportunities to remediate PFAS contamination, but to actually treat, to destroy the PFAS, it's still recognized that high temperature incineration is probably the most effective. Now, there's a lot of evidence coming out, electrochemical reduction, et cetera. But in this case here, what we're doing is we're actually mineralizing the fluorine by combustion at 1,000 degrees plus. And the fluorine is then trapped in an impinger to form hydrofluoric acid, and the fluoride is measured by ion chromatography. Easy peasy. That's the technical term. So the first commercially available example of total organic fluorine analysis using combustion ion chromatography, it was published in 2019 by von Abercron and his colleagues. And what I want to point out here is, if you look at the histogram, they were measuring the amount of organic fluorine and PFAS in wastewaters. And if you look at the histogram, the dark bars represent the theoretical fluorine. If you basically just analyze for the target PFAS compounds and then calculated what the fluorine contribution would be from the totality of the target PFAS, you get these dark bars. And taking a sample and measuring for total organic fluorine, what Van Abercron showed, and these are the lighter bars, is that the total organic fluorine in wastewater was typically 100 times higher than the sum of the PFAS and by extension the theoretical fluorine based on the PFAS results would have suggested. So what it's saying in English is that we're missing a lot. I do want to point out, what do the results mean? They are not directly comparable. When you're measuring PFAS by liquid chromatography with tandem mass spectrometry, you're getting a concentration of the compound. So if you get 250 nanograms per liter of PFAS, does not mean you should get 250 nanograms per liter of organic fluorine. Matter of fact, you should get 162 because the fluorine contribution, as shown in the calculation here from PFAS alone, is about 64.7%. So a good rule of thumb is if you measure your 40 compounds by LCM SMS and sum the concentrations, a good rule of thumb is 65% of that concentration would be represented by organic fluorine, and that's how you would do the comparison. So looking at some real world samples, you can see that in some samples, the PFAS measured is representing the total PFAS based on total organic fluorine. So in the first one, this is a groundwater well where it resulted in concentrations of 6,2-FTS, PFOS, and perfluorohexane sulfonic acid. So if you sum those up, the total is 25.7 micrograms per liter multiplied by well, actually we did the theoretical based on each compound. The total organic fluorine, the theoretical, would be 15.7%, 15.7 micrograms per liter. We actually measured 23. So it's about a 1.5 times the increase. Now that could be variability, but what it's suggesting is that the impact is primarily in these compounds. Another monitoring well, we just saw PFOS and PFX, or perfluorohexane sulfonic acid, where the theoretical is about 2.9, but we actually measured 50 micrograms per liter by combustion ion chromatography. So that's suggesting that there's there's more stuff in your sample than what is measured by the targeted analysis. This one here is the one I love, is Petrosil 3%, is an AFFF. That's one of the main sources of PFAS impact in environmental samples, is the use of the fluorinated aqueous film forming foams or firefighting foams. Now, Petrosil 3%, it was primarily 6,2-FTS. There was probably other compounds, PFOS, et cetera, the lower molecular weight compounds, but because of the high dilution required, what was reported was primarily 6,2-FTS. Based on that concentration, the theoretical organic fluorine contribution should have been about 31,000 micrograms per liter, 31 parts per million. We measured well over 2.5 million. And what that's saying is that there's a lot more in this AFFF than just the 6,2-FTS, which makes total sense. What is really interesting about this particular sample is the MSDS, or the SDS associated that came with the Petrosil 3%, said it didn't have any. And again, being a little bit older, it makes sense to me because the SDS may have been printed well before any concern for PFAS. PFAS, it's still, the jury is still out, although all evidence is pointing at it being a hazard. But you really only have to print in an MSDS what the hazardous components are. So, somebody could be playing semantics games. The point is 53,000 versus, the total organic fluorine, it's well over 80 times difference. So it's saying you're not capturing all of the PFAS. These are actual samples from a site, obviously, redacted, but what it compares is combustion ion chromatography versus total organic fluorine using the TOPS assay. And so you can see that total organic fluorine in some instances is consistent with the TOPS assay. So what that's saying is the TOPS assay is capturing all of the PFAS, but in other instances, the two bars to the left, or to the right rather, in each triplet, the first bar is the TOPS assay. The other two bars are combustion ion chromatography. What we're doing, we were playing around with different preservatives. But the point is that in a number of these samples, you're getting substantially higher potential total PFAS, or substantially higher total PFAS by combustion ion chromatography than the TOPS assay. And it's you know, as is suggested as one of the limitations, is you may not be capturing all of the precursors using the TOPS assay. Here's another compelling example, and this is looking at activated carbon, waste activated carbon used in the remediation of PFAS contaminated water. If you measure the target compound PFAS, that's this little blue thing down at the bottom. Total organic fluorine would suggest that there's a lot more that's being missed using the LCMSMS analysis. Again, another example, in some cases, the theoretical fluorine from LCMSMS is consistent with the total organic fluorine by combustion ion chromatography, but on the very far right, looking at a stormwater sample where there was a recent AFFF release, fluorinated firefighting foam, if you looked at just the target PFAS, you'd be missing an awful lot. So if we refer back now to the complex questions that needed to be answered, or that need to be answered with respect to PFAS contamination, PFAS by LCMSMS, it provides target compound concentration. So if you know what you're looking for, this is the approach, because it gives you accurate concentrations of the individual compounds at trace levels. The TOPS assay provides the same, but it also provides a glimpse into the magnitude of the other 4,960-ish compounds. Whereas total organic fluorine by combustion ion chromatography provides a measure of the total PFAS impact in a sample. Each of these techniques offer distinct advantages and disadvantages. Target PFAS by LCMSMS and the TOPS assay provide accurate concentrations of individual compounds at the part per trillion and subpart per trillion concentrations that are required in most jurisdictions to demonstrate compliance with regulatory criteria. The TOPS assay also affords a glimpse of PFAS impact beyond the 30 to 40 compounds. Total organic fluorine by combustion ion chromatography provides a far more accessible and cost-effective approach to measuring total PFAS. Now, the limitations of PFAS by LCMSMS and the TOPS assay include high cost. There's a high capital cost. The standards, the isotopically labeled standards, are expensive. The level of effort is much higher than, for instance, a hydrocarbon analysis. There are certainly longer turnaround times, and they only test for 30 or 40 individual compounds out of a potential 5,000 plus compounds. Total organic fluorine by combustion ion chromatography, while it's cheaper and faster, it's a non-selective test. So for demonstrating regulatory compliance for PFAS or PFOS in drinking water, not the approach, unless you can demonstrate that PFOS is your only compound. And it is limited in sensitivity for the moment. Where efforts are ongoing in our laboratory to improve the sensitivity of the technique, thereby decreasing the reporting limits. Right now, we are at 600 parts per trillion in water as a reporting limit, and 200 to, well, it's actually now at between 1 and 200 parts per billion total fluorine in soil. So where does total organic fluorine by combustion ion chromatography fit in the analytical toolkit available to environmental practitioners? If you are trying to demonstrate compliance with regulatory standards, and these are based on individual compounds, hence a targeted analysis is required. When you're considering site characterization is typically based on individual compounds as well. Therefore, measurement of PFAS by a targeted method is most appropriate. And this includes the TOPS assay. If you're trying to characterize it just for total PFAS analysis, for total PFAS, it doesn't tell you much about what is contaminating your site other than its PFAS. When you consider contaminant delineation on a site, contaminant delineation is typically performed with targeted analysis. But if you are trying to delineate the PFAS individual compound contamination, obviously a targeted analysis is what's required. If you're trying to delineate the extent of PFAS, so the per and polyfluoroalkyl substance contamination, then you need to be looking at something like the TOPS assay or total organic fluorine. And this, again, becomes important if you're trying to mitigate future risk and liability. But the TOPS assay and the total organic fluorine it'll certainly provide a more comprehensive delineation of PFAS impact. Now, if you're trying to establish the completeness of remedial action or an assessment of future risk or site risk, if you're remediating for individual compounds, then sure, you could use PFAS by LCMS-MS. But if you're trying to remediate the extent, the totality of PFAS impact, you have to be looking at more comprehensive analysis, something that either gives you an indication of other PFAS compounds, or like I say, if you can measure total PFAS, that is the way to go. And the same goes for establishing future liability. You have to understand those compounds that are beyond the scope of the target list that can transform. And then more and more often now, certainly from an environmental standpoint, but increasingly from the standpoint of labeling things like consumer products, when can you say that a sample is genuinely PFAS free? And that's when there's no total organic fluorine present. So with that said, that concludes my presentation. Here I've provided contact information on the right if you require additional information, but also one of the great pleasures of my job is I get to engage with some really, really smart people, both within the laboratory and amongst our customers. And I do want to recognize the folks who did a lot of the work developing and commercializing the total organic fluorine test within our laboratories. Primarily Adam Robinson and Heather Lord, Dr. Heather Lord, who has managed our R&D activities. So on behalf of Bureau Veritas, I thank you all for your attention, and I welcome any questions that you may have.
Thank you, Terry. Thanks as always. Anyone have any questions for Terry? Somebody must have a question.
The slide deck will be made available, correct, Joe?
Yeah. It's the same one you gave at RemTech, basically,
Yeah.
right?
Yeah.
So I'll be sending out the links later today. So, and you can contact Terry directly there because his contact info's on there.
Absolutely, and I welcome any questions, any inquiries. Just want to talk about the technical considerations as well. Feel free to reach out.
Okay. I see no questions, so we'll move on to our next presenter. And Terry, you didn't run over. I'm impressed.
So am I, to be honest with you. Again, thanks everybody for your attention.
Our next presenter is Michael Lupart of Trace Associates.
Hello. How are you
Hello,
doing, Joe?
Michael. Good. I just sent you, you should have a link to share your presentation.
Perfect. Here, I'm going to try.
And Michael's going to speak to us today about an abandoned dry cleaner brownfield in rural Alberta and the costly and dangerous family legacy that it left. So we'll get Michael to bring up his presentation and we'll get going.
There, Joe, can you guys see that?
No, we can see your email or your.
Well, here, I can close that. Excuse me, guys. How about now?
Yeah, now just go to the display settings at the top left and switch it to swap presenter view. And we're good.
There we go. We're laughing. All right. Well, thanks for having me again, Joe. As always, it's great to chat. And even if it's virtually, we can't do it in person, but I'll try and make up for it by keeping it a little bit light and exciting as much as I can. Yeah, wanted to present to you folks, if I haven't met you at the RemTechs or EnviroTechs in the past, about an abandoned dry cleaner in rural Alberta, a costly and dangerous family legacy. Yeah, pretty sensational title, but yeah, it's a really interesting site, really great opportunity to work with the clients on it, as well as be able to kind of work through some pretty interesting and what I found to be kind of unique opportunities. So this is a background, an overview of what I'm going to be discussing. In general, quick background, our initial response, assessment, decommissioning, remediation, and then kind of leading up to the end, the finish point there in the property transaction, and then sharing some learnings and have a couple minutes for some questions at the end. So interested to hear your thoughts, but I'll dive right into it. So this is our site. Abandoned dry cleaner in rural Alberta. It doesn't look like much. It's about 1,000 square feet. Maybe a little bit of the history on the site itself. It was a dry cleaner laundromat until the early 2000s. You know, generally occupied from the 1940s when it was constructed until today. It wasn't a full dry cleaner. It was about 1,000 square feet, and the top of the main floor was the dry cleaning operations, and then the basement was actually a residence. And this was a family of 4 that lived in the basement. The family had immigrated from China in the early 1900s and continued to expand their holdings in the town. You know, it started off with a dwelling, and then it turned into a laundromat, and then it was a dry cleaner, this site, as well as a couple other properties. And this was Let's see if I can switch to the next slide. There we go. So this is a picture of the inside of the dry cleaner after a little bit of cleanup, believe it or not. But this is a photo looking out the front door. So that last photo was looking towards the front door from the outside. This is what the inside looks like. No occupancy since 2000. The biggest reason for that was there was a quite tragic, actually. There was the gentleman that occupied the dry cleaner and was responsible for the operations. His daughter was murdered, and this gentleman then spent the remainder of his life and shut down his company to track down those people and bring them to justice, which he did. But if you're wondering why someone could just up and leave one day and leave everything as is, that's a pretty good reason. So no occupancy since 2000. It was really like stepping back in time almost. As with no occupancy, there was no one looking after the property. There was a local site contact that had a set of keys and kind of kept an eye on things. But what made it interesting, in around 2012, there was a flood because somebody stopped paying the heating bill, but they were still connected to the water. No one noticed the flood until a neighbor actually called the fire department because there was water leaking into their basement from the basement ceiling, and they found that there was about 6 feet of water in the in this building in the basement. And so they think it had probably been filling up with water for about 4 months. And then they were able to start paying the heating bill again, drain the water from the basement. There hadn't really been any remediation or any kind of activities other than just moving some things around in the basement out of the way. But the property still remained untouched until around 2015. And then Trace got a call. As it happens, I think it was a Friday of a long weekend at 4 o'clock. And the family had reached out to Trace, and they were actually the executors of the will, and the matriarch who was responsible for these properties had passed away, and the son and the daughter now were responsible for kind of executing, identifying the assets, and trying to figure out how to wrap up the will. The family didn't understand initially that they had owned this property or even were responsible for this property. They thought they had divested it to another family member years ago. But within that phone call, we quickly understood with the lawyers that they were wholly responsible for this site and cleaning it up. So we said we could help. But first question is, where do we start? And the most basic question was, can we even get into the property? Is it even safe to go in here? And that was always top of mind for us, was the health and safety considerations. So came up with a little bit of a game plan. First thing we did was talk to a structural engineer and say, you know, can we access this property? They did an assessment and said, yes, you can. Health and safety considerations, look at there's a whole bunch of chemicals that we could see even from the windows, and then also mold. You can actually see the high water mark by the dinosaurs in the basement there. Yeah, there's mold throughout the entire basement, a whole bunch of chemicals, unknown chemicals throughout the entire property. But then the other thing is, you know, where we start, but then also trying to understand with the clients where we finish. What does the finish line look like? You know, their questions were initially, well, how much is this going to cost and how long is it going to take? To which I responded, I don't know to either of those, but it's going to take some time. And then it was more about, well, can we actually divest this property? Is this going to bankrupt the estate? What are the ethical obligations associated with assessing and remediating and decommissioning this property? And I'll touch more on that here in the next few slides. But in terms of entering the building, first things first, we did some air sampling just to make sure that we were able to access it. We still wore PPE, specifically goggles, as well as some specific vapor cartridges and gloves and Tyvek suits anytime we went in there. But that was the first step, figure out what we're trying to deal with here. And this is a little bit of a snapshot of what we're dealing with. A whole bunch of buckets with stuff in them. Some of them were empty, a lot of them were empty. Some of them had some chemicals in them. Those of you that are familiar with dry cleaners, you know what we're typically looking for. You got your perchloroethylene or your tetrachloroethylene, whatever the kids want to call it these days. We'll call it PCE. You got solvents. You got your waste products there. That's on the right-hand side. Those bins and bags. And then we've got all these other unknown, just household chemicals and dry cleaner chemicals, or just operational chemicals. So the first step we wanted to do was to try and understand what the chemicals were, how we can appropriately dispose of those chemicals, and led us to the majority. Oh, this picture looks a little strange, but this is a picture facing from the front door towards the back of the dry cleaner, and found out there was about 200 of these barrels. All of them were empty because they had been there for years, maybe decades. All of them contained PCE. A couple of the lubricants and the solvents and the other household chemicals that we had, we were able to collaborate with the local fire department and dispose of those chemicals at their facility. But these industrial chemicals, actually all these empty containers, I'll get on to how we dispose of those in a little bit. But first, it was trying to characterize what's actually in these things. This is a picture from the back of the laundromat So the back door looking towards the front door, follow the light. You can kind of see these are those typical racks you have for any dry cleaning business where you hang your shirts and your jackets from. This was after a little bit of decommissioning already, because we had removed all these jackets. There was about 1,000 shirts and jackets that were hanging on these lines. Like I said, it was walking into kind of like a little bit of a time capsule. Some pretty cool jackets from the 80s there from a security company that no longer exists, but that's another story all in itself. There's fur coats too. There's some leather pants, which I took home and can model those at a request. Just kidding. And then from here, we kind of get a sense of some of the chemicals. You can also see the dry cleaner machines themselves. And then you can also see this big safe right in the middle here. I'll touch more on the safe in a few minutes. But that was the other big question. Once we started to get a handle on, okay, how do we get rid of, how do we recycle or reuse or remove the debris, whatever the debris entails, whether it's the chemical containers, the facility equipment, the jackets, the clothes that are dry cleaned. What do we do with the dry cleaning machines themselves? And I'm pretty comfortable. I'm very comfortable doing soil and groundwater contamination, some air assessment as well. I've never dealt with decommissioning a dry cleaning machine. And this is one of the first big learnings is, if in doubt, reach out to a professional. And that's what we did, is we contacted a local expert. It was actually a peer competitor locally that knew the family quite well. And did dry cleaning in the area, and was very familiar with the machines and the installation details and the decommissioning requirements, and was able to come up with an agreement whereby they would decommission these dry cleaning machines. These are the other two dry cleaning machines. They were able to remove them from the property using some special equipment and recycle the dry cleaning machines themselves. They were able to capture about 80 liters of PCE from within the machines that still existed, and actually take that material off site to a special disposal location. Because this is hazardous waste, it's got special disposal requirements. And then they were also able to take about 40 of those filters that we saw in the basement and then take those for appropriate disposal as well. So we're starting to get a handle on the inside of the building. The other big concern, we're starting to get a handle on the chemicals and the hazardous building materials that might be in there. The other big one is the environmental component. So what are the soil and groundwater conditions like? How are we going to assess that? There's actually had been some previous environmental consulting work. You can see the old groundwater monitoring well on the soil bag here. This is a picture at the back of the building. And you can see there's not much to see here, a couple doors, but then in the bottom left corner there, there's a half buried barrel. And what's against the wall was the next question. And this was, I think the person helping us decommission the dry cleaning machine said it was a sump, but it was a system that was connected to the dry cleaning facility itself, connected to the machines, whether through off-gassing or vapors to help control or mitigate that. But aside from the obvious issues there, trying to understand where could some of the soil and groundwater contamination be? Is there soil and groundwater contamination? I guess that's the first question. I've never met a dry cleaner that didn't have impacts, so it's kind of almost assumed, and if not, it's likely an environmental concern or a potential environmental concern. But let's go through the process and actually figure out, are there other environmental concerns that we have to capture as well? So how are we going to do that? Good old-fashioned contaminated site assessments. Previous environmental reporting. Let's go through a phase 1. Let's do a phase 2. Previous environmental reporting. Like I said, there was a previous phase 2. We received the report, and the objective of the reporting wasn't quite clear, but the assessment methodology was to go out and install, do some boreholes and groundwater sampling and assess for petroleum hydrocarbons. So there was non-detectable hydrocarbons, but it was good information to have in terms of the monitoring well construction details, because now we knew where the shallow groundwater was, and it was around 1 meter and 1.5 meters below grade. So we incorporated those results into the phase 1 environmental site assessment that we did, and that included, historical site owner interviews, looking at adjacent surrounding properties to see if there's any other potential environmental concerns outside of just the typical dry cleaner here at the site and the operations, the historical operations. And we ended up that the primary focus was going to be the dry cleaner and the historical operations there at the site. In terms of the surrounding area, not a lot happening. And so we were able to focus our assessment, soil, groundwater sampling, inspecting the pipeline systems, because as you're well aware, historical dry cleaners, the methodology historically was to, if you didn't want to dispose of the chemicals appropriately, was to dump them out the back or pour them down the drain. The drain was in the basement here, and wanted to just kind of get an understanding of if that could have been a potential environmental concern in itself. But regardless, further soil and groundwater sampling was recommended. So we initiated a drilling program, installed some nested pairs. Luckily, this site is very tight clay till material, all the way down to the maximum depth of around 12 meters. We found the shallow groundwater zone at around 1 to 1.5 meters. And then there was another deeper groundwater zone at around 8 meters. We did some hydraulic connectivity analysis to support the development of these site-specific guidelines. Values were 10 to the -8. We were able to look at some of the applicable pathways, the exposure pathways, a lot of PCE and a lot of the associated chemicals. We call them daughter products or byproducts. You've got your vinyl chloride, your chloroform, your cis, your trans, 1,2-dichloroethene. A lot of those are controlled by the FAL and the DUA pathway. And then the next limiting pathway is the inhalation pathway. So we did some work around eliminating the FAL and the DUA pathway to allow us to bump up those guidelines. And what we were left with was impacts in the shallow groundwater zone, as well as the soil. Had really good data to suggest that the soil impacts, though, were quite limited. It only went down to about 4 meters. It didn't have any detectable concentrations in the soil past around 5 meters, and then there was nothing detectable in the deeper groundwater zone. So kind of gets us to our next stage. What are we going to do with the soil and groundwater contamination? We're gonna tackle that through remediation, and that's going to be excavation. But let's flip back to the inside of the building here, and let's figure out how we can clean up the inside of the building before we start to do our remedial work. So we started doing some decommissioning. And again, top of mind, health and safety considerations. How can we do this, ensuring the protection of our employees as well as the public? We ended up talking to the local landfill and asking them what we can do with these barrels, these old empty barrels. And through a lot of collaboration, we were able to come to the conclusion that we could take these barrels to the local landfill and actually recycle them. But the plastic was recycled, but the metal was also able to be recycled in the general scrap yard. So this is just a picture of us loading it up and hitting the road. And this is where we took it to. All in all, there's about 200 barrels that we ended up removing from the site. And so now that we've got kind of the bulk of the chemicals out of the way, aside from the mold, what can we do with everything else? And as you remember, the facility itself, the top of it was a dry cleaner. The bottom of it was a residence. So not only do we have to consider all the dry cleaning facilities and everything else, but anything that you would expect to find in somebody's home as well. Keeping in mind that this stuff had been underwater for about 6 months, 6 to 8 months, and then left as is for another 5 or 6 years. So we started hauling the material out of the back of the building and took it into these waste containers, where we took it to another location where it was sorted and recycled or potentially reused. And then that was one of the interesting parts within some of the community engagement, had a local Hutterite colony reach out to us and actually ask if they could take some of the old dry cleaning machinery, none of the stuff with chemicals in it. A lot of it was related to the ironing machines they had, or the automatic ironing machines. And we were able to effectively donate that equipment to the colony so they could use it. We disposed of material where we had to. We tried to reuse or recycle material as much as we could. All in all, we ended up pulling out around just under 2 tons of material. How do we do it? Good, honest work. That's me, as well as my poor colleague Kirk that helped with the efforts. This is us standing near the front door of the dry cleaner, looking out towards the back. You can see it's already starting to clean up. Yeah, just because we have time, I'll maybe dive into one of the fun stories within the basement. So if you remember, it was a residence. We came across a freezer, this capacity of about, I'll say 200 liters. And I see liters because if you remember that the power shut off, the area was flooded, it stayed underwater for about 6 to 8 months. I pulled the short straw on the task of cleaning out the deep freeze. So I had to take about 200 liters of liquid-ish material out of this deep freeze and haul it to an appropriate disposal facility, which was the landfill. We were wearing specific respirator masks, so I wasn't able to capture the scent. Yeah, it maybe a little bit of post-traumatic stress coming out of it. We did have one complaint, and that was from the adjacent landowner while we were doing this work. The only complaint that we had, and it was an odor complaint. They came over and asked us what the heck we were doing, because apparently some of that freezer stuff, one of the bags had caught a nail and it leaked a little bit onto the ground. So we were able to clean that up and address any potential concerns, but it was interesting and unique considerations while we were doing the work. This is a picture of it almost cleaned up. You can see there was some older facilities there in the back corner. It's an ironing board, and again, the local Hutterite colony took that material away. And then we were left with some other things. And outside of all the typical stuff you'd expect to find in a domestic in a domestic dwelling as people live there, we ended up finding 5 safes. And this one in particular in the middle here, was probably a ton in itself, and we couldn't move it. So we're trying to evaluate how we're actually going to move this safe out of the area. We ended up pairing that up with some of the remedial work that we're doing, and we were able to pull the safe out the back door. We ended up donating the safes to a local locksmith, saying that they could keep the safe, they couldn't keep the contents. Unfortunately, they didn't find anything exciting. I wish, they would have found a whole bunch of buried Roman coins or Bitcoin or something like that, but no luck. We ended up finding a code to one of the safes, and then a whole bunch of piano recital tapes. And that was kind of an interesting discussion, because I'll get to it here in my lessons learned, working with the family, trying to understand what's important, what they want to save, what they want to keep, while we're going through this process. A lot of consultation and collaboration. And then the sense was, if in doubt, throw it out, or if in doubt, give it away, recycle it somehow, because the family, they'd been getting on in their years as well, and they lived in a small condo or 2 small condos, and so they didn't have a lot of space for a lot of this extra stuff. So now we got the inside figured out, or as much as we can, and now it's on to the remediation. Again, health and safety considerations for those of you that have been blessed to be able to work in an urban setting. A remedial work is the same as it would be in anywhere else. It's a little bit smaller, it's a little bit harder, and it takes a little bit longer, and it's usually more expensive. You can get a sense here that we're working over overhead facilities. There's some underground utilities that come right out the back of the building here. There's the public considerations, as well as some engineering constraints, because we're digging next to these buildings. So got a picture starting to hydrovac some gas lines. There's an active gas line, there's an abandoned gas line. Started our excavation here. This is the abandoned gas line that runs through the center of the excavation. We got approval to remove that. Thing here you'll notice is that some of the excavations are sloped. There's one wall that's sloped at a 45-degree angle, one that's kind of straight walled. Work with a structural engineer to understand where we could dig next to these buildings without impacting the structure of the buildings themselves. This is us loading up some of the material. All in all, about 300 cubic meters of material we hauled out of the property. We were able to get the resulting excavation boundaries to meet the site-specific guidelines that we developed. And then we were approached by a local contact who wanted to purchase the property. So they ended up doing a third-party environmental review. I don't know who did that environmental review, but they did leverage another environmental consultant. There was consultation between the lawyers in terms of back and forth on what this environmental reporting means and what it could mean for potential or perceived and future environmental liability. And after a significant discount from the property value, they were able to come to some kind of transaction, and it was closed in 2017. And then the executors of the will shortly after that were able to close up the will. So learnings from this, take your time. It's a good thing it wasn't rushed. It took about 2 years to get through this entire process. Understand the process or find someone who does. Like I said, I'm not a dry cleaner, decommissioning expert. Consult often, especially with any of the stakeholders. The client representatives, and then don't assume. What I meant by that is that I assumed that we were trying to keep the legacy intact of all these special particular things that we were finding, but a lot of times it was just make sure that goes to an appropriate location for disposal. And yeah, that's about it for me, guys. So thank you for your time. Feel free to open it up to any questions or comments. I'm not sure, Joe, if there's a chat.
We're taking questions. So if anyone has any questions for Michael, please drop them in the question box. We'll get to them. Michael, with my love of abandoned buildings, that safe is pretty awesome. I've seen a few of those in my times. I don't think people realize the risks and the challenges of going into some of those buildings. I was just recently, about a month ago, invited down to a hotel in rural Alberta, a 4-story one that's 100 years old that was being demolished. Asked if I'd come in and take some photos before the crew came in, and I'm glad I listened to their advice of bring some gear because you're going to need it. And when I got up to the 3rd floor, it was 3 feet thick of pigeon parts and excrement. It was something to behold.
Yeah, I can only imagine. And you're right, because it's even entering the building on the first day. It was like, can we even go in here? I don't think we can. And, the family had been going back and forth, and they'd let people in to come and grab some personal effects or some clothing if they were like, hey, you haven't returned my dry cleaning in 7 years. Give me back my leather jacket. But that was my first thought as well. I mean, it was pretty interesting sight.
I at least had, in this case, had the company that was doing the work had cleared a safety route through, so at least it was good to get in. Like, there was a way to get in and get photos, but you can imagine a 100-year-old hotel, what kind of shape it was with water damage and mold and all other parts of goodies. But I do have a question for you from one of our listeners. How do you address impacts below the building? Also, were there any groundwater impacts to deal with?
Yeah, great question. So the impacts below the building, we assess them through doing the evaluation of the water line and the sanitary line. But that was one of the limitations, because the building itself on 2 sides was surrounded by other buildings. So we were able to access two parts of the building. But as always, that's one of the gaps, within the remediation itself. We were able to prove that we got clean remedial extents within the soil, but had to be careful in terms of how we presented those results to a third party. And then similar to the groundwater, we were lucky in this instance, the shallow groundwater, effectively remediation through excavation. and confirmatory sampling. And then we still had the backup of the deeper groundwater zone where we were able to prove that that in fact was non-detect.
Great. Okay, I don't see any other questions at this time, Michael. Michael's contact info is on screen, and I'll be sharing a link to where the presentations are afterwards, so you can find his contact info from the video that I'll share or the presentation. So thank you again, Michael, and we'll move on to our final presentation of the day.
Thank you.
Up next is Rick McGregor of In Situ. Rick, I just shared the link with you to share your presentation. Great. And Rick's going to be speaking on a summary of 4 applications of colloidal activated carbon for the in situ treatment of PFAS in groundwater. So over to you, Rick. Rick, you're muted.
Oh, sorry about that. Can you see
No
my screen,
problem.
Joe?
You're good. You're good now.
Okay, good. So I'm Rick McGregor, obviously. I'll acknowledge 2 of my co-authors, Natisha Benito and Alex Zal. I'm going to summarize fairly quickly 4 studies done for the in situ treatment of PFAS. These are kind of the first 4 ever completed in the world, and are kind of the basis of most of the in situ work being done right now for activated carbon. So we'll just get on there. I won't give too much of a background, as Terry gave a good background on PFAS themselves, but as most of us know, they are considered emerging contaminants, even though they've been around for 30, 40 years now. They are very complex chemically. As Terry said earlier, there's probably over 5,000, and even that number is, you see that vary by a couple thousand different references. The reason they're a real concern for environmental is the carbon fluoride bond is very strong, and it's very hard to break chemically and biologically. So they're very persistent. There's studies that have been shown they bioaccumulate, at least some of them. A lot of the toxicology for most of the compounds hasn't emerged yet, so that's very much ongoing. As Terry indicated before, there's lots of analytical challenges. One is because there is so many of them. 2 is as we have to detect to very low parts per trillion levels for the standards or treatment standards. And from an environmental point of view, we have to remediate to, in some cases, below 10 nanograms per liter, which is unheard of in most, when you look at most of our contaminants we have to treat. That said, a lot of stuff is still emerging, the fate and transport. We really don't understand how a lot of these compounds behave in the subsurface. Some of them have very unique properties, like some behave as surfactants, some prefer the air-water interface. So it kind of, a lot of conceptual models being developed right now are trying to address these issues. Oops. So right now, most PFAS in groundwater is addressed by pump and treat methods. And that means pumping them to the surface, collecting, treating the water, usually using activated carbon or ion exchange resin. Those are the 2 processes used commonly now. There's other ones being developed. Probably the most readily for commercialization is foam fractionation, but there's plasma, there's thermal methods, but those are still kind of emerging and still being tested. From the in situ point of view, there really is only one technology out there right now that's being proven in the field, and that's using activated carbon, and specifically colloidal activated carbon. Activated carbon can come in 3 different forms. One is the granular activated carbon, which most of us are familiar with, which is used in water treatment. It's very coarse, it's sort of like a sand, and it's very well proven, well used, and very good on organic compounds. The problem with that is it's very hard, if not impossible, to inject into the ground properly. So there's 2 other forms, powdered activated carbon, which is about 100 to 200 microns in diameter. It hasn't really been shown to be used for PFAS in the ground yet. I'll present some studies here that we looked at using it. And then there's the colloidal form, which is about a diameter of 1 to 2 microns. So it's the size of a red blood cell. So it's very fine. And that's great from an injection point of view because it really goes into the ground almost as easy as water. That's what I'm going to present today, some of the case studies done with that. Other technologies being developed for in situ are ion exchange resin. That's being worked on in the States at a couple of universities. Biochar, AECOM has did some work on that. As I said before, powdered activated carbon, and there's foam fractionation, chemical oxidants, and solid chemical, which are very much in their infancy for in situ treatment. So we'll get right into the sites here. The first site is a petroleum hydrocarbon spill that was, we were retained to clean up the petroleum hydrocarbons in the groundwater. The source had been excavated already, but there was residue petroleum hydrocarbons in some soil as well as the groundwater, so we were retained to address those. So the BTEX was about 300 micrograms per liter, and F1, F2 were 2,000 and 3,500 respectively concentration. So not fairly significant concentrations, but not dreadful. Just before we were starting the cleanup, the consultant informed us that there used to be a fire training area here. So this happened about 6 years ago now. And so I just ran around and grabbed some samples. At that time, we were really only, commercial labs were only really able to analyze for PFOS and PFOA. And so I grabbed some samples and submitted those. We did our cleanup for the petroleum hydrocarbons, and that cleanup was a combination of colloidal activated carbon along with oxidant releasing materials. After we did the cleanup, we got the results back for the PFAS, and they showed there was PFAS and PFOA both present in the groundwater. So the aquifer itself was a silty sand with some sand lenses, which is always a challenge for in situ methods. It was unconfined with a velocity of about 1 meter per day. The design was based on direct push technology, so using a geoprobe where we would advance rods that you see in the right-hand picture there down to a certain depth, and you would inject the reagents of your choice into those rods. Use a density, injection density of about 3 meters for the grids, and then we do multiple locations at multiple vertical intervals. We use low pressure, less than 25 psi, and put a small volume in each point to maximize surface area and dispersion reactions. So this is one of the more boring graphs you ever see for remediation. The blue and red graphs, bars here represent the pre-remediation concentrations of the PFOS and PFOA. And then afterwards, and this site is now 5.5 years old and being monitored for at least semi-annually for over 5 years now, has showed that none of the PFAS or PFOA or any other actually PFAS compounds have actually been detected in the groundwater since remediation. So this is actually the longest studied site in the world for in situ remediation. And it was done near Ottawa, Ontario here. And so the results of this study spurred a whole bunch of additional studies. This site, the limitations with this site was it was a relatively simple hydrogeologic system. Even though we had greater 5 years removal of PFAS and hydrocarbons, both the hydrocarbons PFAS, it was still not really well defined from a PFAS point of view. Now that said, Dr. Grant Clary of Portwater Solutions did some numerical modeling, and from the isotherms and that were used, they calculated that the activated carbon that was injected would last for at least 50 years, assuming the source was still present. So everything pointed to this being a very promising technology, and the modeling suggested it could last a long time. But that said, this was the first and at the time the only study done. So this spurred a whole bunch of more studies. If anybody's interested, these two studies have been, the modeling and the field study have been published in the Journal of Remediation. If you need a copy, you can go to their website and get a hold of me. The second site was a large petroleum hydrocarbon distribution facility in the Middle East. They had a large BTEX plume from the facility. This is one of the, probably the largest BTEX plume in the world, actually. And as part of the facility, twice a year, they practice firefighting at the facility. And with the firefighting, they use the foam, AFFF foam. So AFFF foam contains PFAS. So we picked a small area within the plume that had concentration about 700 micrograms per liter and gas range and F1 range about 3,500 micrograms per liter, and we analyzed the groundwater for PFAS. We detected 6. I won't get into the alphabet here, but some of you will recognize some of these names. So we detected PFAS with 4 carbons right up to 12 carbons. The most common being the 4, 6, and 8 carbon chain ones. And you'll see we've seen up to about 24,000 nanograms per liter. So moderate concentrations, not overwhelming, but still significant. So this geology of this site was a fine grained sand. And once again, we had a typical lens about 1 inch thick or 3 centimeters thick of medium coarse sand, which we were afraid that would create a preferential flow pathway. So we were conscious of that during our injection program. It was an unconfined aquifer with a groundwater velocity about 60 meters per year. As you would expect in a petroleum hydrocarbon plume, the geochemistry was an iron sulfate reduction geochemical condition. So at this site, we did something unique. The client wanted us to look at 6 different possible treatment methods. So we set up 6 permeable reactive barriers or permeable reactive zones, whatever you want to call them. And within each zone, we tested a different type of reagent. The diagram on the right there shows the typical setup for each permeable reactive zone. So the black dots represent the injection points, which were done on about a 1.5 meter grid. The shaded gray is cores that we took to look at the distribution of carbon before and after injection to make sure we're getting good distribution of the reagents themselves. And then we had both traditional 2-inch wells installed up gradient within and down gradient of each PRB, as well as what we call CMTs, which are multi-tube, multi-screen specialized wells that give us 7 monitoring points throughout the aquifer, so very detailed vertical monitoring. We also did a lot of hydraulic conductivity tests for each one to get a good idea of vertical hydraulic conductivity, and as well as the lateral variation hydraulic conductivity. So the 6 compounds we tested here were colloid activated carbon, a powdered activated carbon, a biochar, ion exchange resin, and 2 oxidants. The oxidants I won't get into just because we weren't expecting them to treat. Most of the literature said oxidants are really not that effective at PFAS, but the client wanted to look at that as well as look at its treatment on the petroleum hydrocarbons itself. So we did do sodium persulfate as well as hydrogen peroxide. The sodium persulfate was unactivated because the groundwater at this site actually had a natural groundwater temperature of about 27 to 30 degrees Celsius. So it was a very warm groundwater, especially for us in Canada. And then once again, the reagents were injected using direct push technology on a grid based, both vertically and laterally. So here's the results for the colloid activated carbon. The graph here at the 0 is the date of injection. So you see the pre-injection concentrations, and I just picked 3 PFAS compounds as C4 up to C8. And then post injection at 90 days sampling out to about almost 2 years of sampling, we see non-detect concentrations of PFAS, and continued sampling, and that shows the same. We haven't detected PFAS in this PRB since. For the other 3 absorbents, being powdered activated carbon and ion exchange resin and biochar, we've seen after 90 days, we've seen the removal of all the PFAS like we did in the colloid activated carbon, but then we started seeing breakthrough of individual PFAS compounds. And generally speaking, we've seen breakthrough of the C4 to C5 PFAS compounds before we've seen breakthrough of the C8, C9 PFAS. And that's kind of expected because generally speaking, the more carbons that a compound has in it, the better it absorbs to absorption media. The real surprise here was the ion exchange resin. We thought we'd get very good results with the ion exchange resin, but the reality is we've seen breakthrough with all 3 PFAS and all the compounds after about a year. We think this is due to the grain size of the ion exchange resin. It's a fairly coarse reagent, and therefore when we analyze the cores afterwards, we see very preferential accumulation in the coarse seam sand, which probably hindered the treatment ability of the ion exchange resin. Since then, we've tried a finer grain ion exchange resin, which has performed a lot better. So the results of this study showed that basically we had breakthrough of all the PFAS and all the reagents except for the chloride-activated carbon. The hydrogen peroxide and persulfate did not perform well at all, and actually in some cases actually oxidized precursors, so that we're actually detecting higher concentrations of some of the PFAS in the samples after application. Generally speaking, the more carbons in the PFAS compound, the better it absorbed to the absorption reagents. Sulfonates absorb better than carboxylates. And then just down the bottom, sort of our relative scale of which perform best with the chloride-activated carbon, performing a lot better than hydrogen. Once again, this study has been published. It was published last year in the journal Remediation. So if anybody's interested, they can once again contact me or go to the Remediation Journal website. The third site was a site in China that we did. It was a commingled plume with TCE as well as the TCA breakdown products of cis and vinyl chloride. You see the concentrations there. Once again, not great, very high concentrations, but high enough. When we analyzed for the PFAS compounds, we've seen 5 were detected, and once again, a range from the low end, the C4s, right up to the C8, C9 PFAS compounds that once again at moderate concentrations. The geology once again was a silty sand in an unconfined aquifer with a groundwater velocity about 9 to 10 meters per year. And as you would expect in our TCE plume, we did see iron sulfate reducing conditions. So here's a couple of the wells within and immediately down gradient of the injection area. And you'll see here for the TCE and the chlorinates, basically the red dots here are the TCE. You'll see that immediately after injection at day 0, the TCE in both wells decreased to non-detection limits. And then you start to see the breakdown of the cis and the vinyl chloride slowly degrade and become removed from solution. And by just over a year and a half out at both sites, all 3 TCE, DCE, and then vinyl chloride were removed from the groundwater. The vinyl chloride tends not to absorb well to absorbent reagents like activated carbon, because it's very short chain and it has a low affinity for activated carbon, but it will, and in this case it did. Now we also injected a bioremediation reagent of polylactate, which helped reduce, which helped stimulate the bacteria. We also analyzed here for ethane. We didn't see much change in the ethane over the time frame of the study. When we look at the PFAS within the groundwater, I plotted here 5 of the PFAS. You'll see that once at day 90, the first sampling event after the injection, we've seen complete removal of all the PFAS from groundwater in both monitoring wells that were within and down gradient of the PRZ. So a summary of this one was this was a commingled plume, unlike the other 2 that I first present were petroleum hydrocarbons. This had TCE as well as the DCE vinyl chloride in it, and we've seen complete removal of all the contaminants of concern, including the PFAS. We've seen strong reductive dechlorination conditions generated, and that's because the chloride-activated carbon is contained within an organic carbon carrier solution. And as I said, we enhance that with another organic carbon donor to help create reduction. All the PFAS were removed to below 10 nanograms per liter for the 2-year period of the study. And I don't present here due to time, but we do take cores of the aquifer before and after injection. And in this case, to look at the distribution of the activated carbon within the aquifer, we obviously want to inject the carbon in the zone of contamination and not outside the zone of contamination. And then within that zone of contamination, we want to make sure we have a relatively even distribution of the activated carbon to make sure we get complete treatment. So in this case, when we analyze the samples collected within that zone of the target zone of remediation, we've seen that 99% of the samples collected did have detectable chloride-activated carbon in it, which was good. Once again, this study was published, I think last year, or maybe even started this year. And if once again, if you'd like a copy, feel free to email me or go to the journal and get a copy yourself. So the fourth site that we looked at was a was a residential / commercial property done here in Ontario. It had a fire in the workshop, and the firefighters actually used the foam to put out the fire. The foam unfortunately contained PFAS, and so this created a problem with the groundwater with respect to PFAS, as well as the petroleum hydrocarbons that were in the shop itself that got into the aquifer. This site was a bit more unique, and it was very complex geology-wise. It had basically had a silty sand unit over top of a sand unit over top of a fractured rock unit. The first two we were pretty confident we could treat. The fractured rock had never been, nobody had ever attempted to treat PFAS in fractured rock in situ. So this was the first site ever done for that. And this, but really there was very limited options. And so the client in the ministry here said, let's try it and see what happens. So here is the 5 PFAS that were detected within the 3 aquifers. Once again, moderate concentrations, not overwhelming, but still of concern. We instrumented the site, the one part of the site that we were doing the injection that we really want to study. With the diagram on the right there, you see a cross section. We put a series of multi-level, those are the CMTs, which either had 3 or 7 screens, and these screens are 6 inches each. So within the silty sand and the sand aquifers, they had 6 well screens in it. Within the fractured rock, you can't use these type of wells in those. So we use packer systems in the wells. We only show 2 here, but we actually had 3 sets of packer systems, which isolated 3 fracture zones within the aquifer itself. I'm just showing 2 here because the bottommost fracture zone was actually clear and didn't have anything in it. So we had very detailed monitoring of this site. These plots are a little bit different, but I'll try to walk you through it. So the first plot here on your left is the PFH-XA, and the top plot up here represents pre-injection. Pre-injection. And then this is 6 months after injection. This plot here is 9 months after injection. This is 1 year after injection. What you see here, groundwater is flowing your left to right. And basically CMT1 is upgrading of the permeable reactive zone or the treatment area. And then CMT2, Packer 1, CMT3, and Packer 2 are all within the treatment zone. So once again, you see at the before injection, you see the PFAS is higher in the shallow aquifer and decreases with depth, but it's still within the fractured rock. Following injection, and we injected using direct push technology within the overburdened aquifers, and then within the fractured rock, we use packer systems to inject the colloid activated carbon. You'll see immediate treatment down to below the detection limits in all 3 aquifers at 6 months with respect to the PFH-XA. After about 1 year, we did see breakthrough within the shallowest, most fracture in the bedrock of this compound, suggesting that the activated carbon within that fracture zone had been exhausted. When we look at other PFAS, we see similar responses with after 6 months and 9 months, we've seen after 6 months, we've seen complete treatment. And then after 6 months and 9 months and 1 year, we started to see breakthrough once again in that shallow most fracture of, in this case, PFP-EA. PFP-EA has less carbons in it than PFH-XA. So we won't get into the alphabet, but suffice to say, we were seeing preferential breakthrough within the fractured rock of some of the PFAS compounds. So at this site, we did within the unconsolidated, so the silty sand and sand aquifers, within 3 months, we've seen complete removal of the PFAS, and that's been sustained for now 2 years with no evidence of breakthrough happening. When we looked at the distribution of activated carbon within those 2 aquifers, and you see those graphs on the right at 3 sites that we took cores at, the black, it represents pre-injection and the blue represents post-injection. You'll see that basically pre-injection, we didn't have any activated carbon, which makes sense. And then post-injection, you see that we increased the concentrations significantly. And you do see some variation within the 2 aquifers with that thin dotted line there at about 4 meters depth represents a sand seam. So you do see some preferential accumulation of the activated carbon in that sand seam, but more importantly, you do see distribution of the activated carbon throughout both aquifers, which is what we need for in situ remediation. So 99% of the samples we collected within the consolidated aquifers had colloidal activated carbon within it, which is good. Once again, in the bedrock aquifer, we did see preferential breakthrough of the C4, C5 carboxylic acid PFAS, but we did not see sulfonic acids breakthrough, suggesting that we are seeing preferential competitive absorption reactions happening within that aquifer. That pretty much wraps it up. I'd like to thank our academic partners here, University of Toronto and Carleton University. I forgot to put in University of Waterloo here, but they are an active member. We are working on one NSERC Alliance grant with them, and as well as a ESTCP grant from the U.S. military grant looking at PFAS, and that involves both laboratory and field studies. So those two studies are just starting, and we should get a lot of fundamental data from that, as well as the industrial partners here, ourselves and Dr. Grant Carey at Pore Water Solutions. He's doing a lot of the modeling. And I guess with that, that wraps my presentation up.
Thanks, Rick. Really appreciate that. If anyone has any questions, please feel free to drop them in the question box. So it doesn't look like there's any questions for you, Rick, but feel free to reach out to Rick if anyone has any questions. He'll be happy to answer them. Thank you again, everyone, for attending. A reminder, if you've registered for this series, you get access to today, next Thursday, and the following Thursday. You don't have to re-register. I will be sending out new links for each of the webinars prior to each event. Thank you again to our sponsor, Trace Associates. A reminder that EnviroTech is in April in Calgary, isa.org/EnviroTech. RemTech East is June 1st to 3rd at the Fallsview Casino in Niagara Falls. New event for ESA that'll happen every second year. Call for abstracts is currently out. Encourage you to check that out. And RemTech, of course, will be back in Banff Springs in the fall. So we look forward to seeing everyone there. Big thank you today to Anthony, Joe, Brant, Paul, Dee, Terry, Michael, and Rick for presenting today. Really appreciate it. ESA appreciates your support. To everyone that attended, thank you so much. Stay safe, and we'll see you next time.